النور والبركة، صباح الخير والرضا.
صباح الورد صاحب السمو، كيف حال سموك؟ أهلا وسهرفتنا اليوم.
والله هذه بالنسبة لي شرف كبير حقيقة لا أستحقه، لأنني لست متخصصا كمجمع الفيزيائيين، ولكن أتمنى لكم مع هذا الحشد اللامع من الفيزيائيين العالميين التوفيق. May I turn to English and say that the experiences I had with Professor Abdul Salam all those years ago were particularly intimate in the context of, first of all, the retreat in the foothills of the Himalayas in Natyar Gali, where I think all physical conferences should be held, because they are, after all, conversations. You're not trying to convert the other, you are trying to converse with him and talk to him or her. And in that context also, I want to say that the situation of physics in the Arab world needs obviously a profile. I hope that my contribution today might be of some value, of some use. At 75 years old, I think I have been used and abused by many aspects of personal vanity, maybe of thinking that I can be a common denominator for everyone who wants to progress an issue. I went to Ladakh, for example, and I didn't go personally, I was represented. I found that I had to turn back because the atmosphere at the level of Ladakh in India was too high. And so the invitation from the Royal Geological Society had to have a representative from me. But anyway, how would you like me to proceed, or would you like me to proceed? I'm at your service. So I go back to Ammar and ask you.
Yeah, please. I think Sha'ban will start welcoming the session. Please, Sha'ban.
Okay. Now, yes, we can start.
I started the Ramadan, so I apologize to Sha'ban.
That's fine. but we can just start now, because according to our schedule, we should start now with the opening. Maybe I will do like Prince Hassan. I will start with very few Arabic words first, as this is Arab Physical Society. صباح الخير والسلام عليكم. بحب ارحب بكم في فعاليات انطلاق الجمعيه العربيه للفيزياء، والتي شرفنا فيها صاحب السمو الملكي الامير الحسن ابن طلال، لتكون الجمعيه جامعه للفيزيائيين العرب ان شاء الله، وتاكيدا لدور الفيزياء في النهضه العلميه. ويشرفنا اليوم ان نجتمع واياكم مع فيزيائيين مرموقين معظمهم حاصلين على جوائز نوبل لتبادل العلم والرؤى الرحبة، ونلهم الطلبة والباحثين ليكون العلم أحد أدوات تقدم الإنسانية وتوحدها. Now we convert to English if we have our speakers with us. So let me start with good morning. It gives me great pleasure and honor to welcome you to the Arab Physical Society launching event. I extend my warmest greetings to Prince Hassan bin Talal, as well as the keynote and invited speakers. I would also like to thank the members of the Arab Physical Society, Governing Council, Advisory Committee, Focal Points, and honorary members. The event could not have happened without your participation and willingness to put your trust in us to establish the Arab Physical Society at last. On June 7th, 2021, the Arab Physical Society was established as a non-profit organization with the mission of spreading and promoting physics knowledge to Arab world through improved scientific education, research, and human capacity building. Since then, we have completed the society structures by inviting 2 members from each Arab country to serve as a member of our advisory committee and the focal points committee. In addition, we invited senior professors in our countries to join the society as honorary members. Then we opened the registration process, and we are pleased to say that we received over 400 requests in just a few months, and more than 1,700 participants for this event. After this important launching event with a great Nobel Laureate speakers, we will organize an important workshop on quantum mechanics on the World Day of Quantum in April 14th, a week from now, and I hope you all can join us. As we have a very tight schedule today, I will leave and I will give the floor over to Prince Hassan bin Talal to greet you and kick off the event. Prince Hassan, please.
Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, dear friends, may I start by saying I am not here to speak of topology or chirality. I can barely get my mind, Claudia, around the Max Planck study, but I am here to talk about the art of Islam, language and meaning. That is to say, in the context of a Swiss traveler, Titus Burckhardt, who in his full lifetime, 1908 to 1984, referred to the art of he who wishes to express the unity of existence. I think that what I have before me on the screen is trending toward the unity of existence of Wahdat al-Wujud. Burckhardt made it clear that there are three means at our disposal. One he referred to as geometry, which translates unity into the spatial order. Two, rhythm, which reveals it in the temporal order and indirectly in space. And three, light, which is to visible forms what being is to limited existence. My background is basically historical and interfaith, or between dependence of faith's dialogue. And the concept of ishraq, enlightenment, is very much on my mind when I remember Descartes, who said that if everything in this world is west, where does the sun rise? And the sun in this magical world, sharq, is the east or the orient. East means illumination. Literally, it describes the first light of dawn arising from the east, but idiomatically it refers to the enlightenment of Eastern or Oriental thought. As emphasized by many thinkers, the Orient here is not a geographical term, rather it signifies a philosophical proof from which light and energy emanate. To me, physics in this manner of thinking is a topic that has to bear witness to developments all over the world, and if I may, all over the pluriverse. We often speak of universe, but I think that we are addressing a pluriverse in this context. One more term that has drawn my attention in your enchanting topics is the standard model of elementary particles. Even for a layman like myself, or a Luddite possibly you might call me, as my children often do, because they're light years ahead of me. I mean, my eldest daughter is 54 years old. I'm 75 years old. So why you are listening to a fossil like myself, I don't quite understand, but thank you for that anyway. I would just like to say that we have to summon the image of one of three advocates of the model of the standard of elementary particles to understand them. And as I referred earlier, one of them is my great friend, God rest his soul, Professor Abdus Salam, who is also the generous mentor of our most active physicists. His legacy is still vibrant, not only in Trieste, not only in Tuas in the Third World Academy of Science, but also in Jordan, and in particular for being the initiator and support. I mentioned Natyar Gali earlier, the hill station in Pakistan, but here we associated ourselves with the Petra School of Physics. And the Petra School, of course, it takes its inspiration in its turn from the Arab tribe, the Anbat, and the term Nabat comes from Istambata. He innovated. So they were the great water civilization, or the way to, I mean, even one world civilization in many cultures, 10,000 cultures, according to my late friend, Professor Mircea Melița in Romania. But the Petra School of Physics was worth mentioning because the Petra School was first suggested by your speaker and by Salam during fleeting visits to Jordan in 1980 and 1981. He was soon to take heart with a handful of dedicated Jordanian physicists, some of whom are with us today. And the school was named and succeeded in a short time to establish a certain credibility. And I remember in '82, Salam saying to those who attend the school from the local universities, may I remind them that Arabic was the language of science from 8th to the 13th century. So you are actually having, I'm wearing a butterfly on my tie, you can't see it, the butterfly effect on all of us, particularly that hallowed citadel of the Arabic language, when you are actually contributing to, and I recognize Professor Muhammad Sandouk, contributing to making the Arabic language more the language of men like Ibn al-Kuf, who combined highest traditions of medical knowledge with research in mathematics. Very quickly, I'd like to suggest that the question of development is controversial to many of us. Developing our abilities is one thing, enabling and empowering poor, like Abdus Salam, who got his first scholarship from my late father-in-law, who was then the foreign minister of Pakistan, to go abroad and become the great figure that he is and was to us. Scientists, I feel, have in brief the duty to pursue new knowledge and new technology and think about how we may pursue wisdom in scientific endeavor. Wisdom, to be put in context, I'd like to say that we are scared of ecosphere and ecocide. As my dear friend, Professor Evelyn Lindner put it, Norwegian-German professor, who is concerned with human dignity. We are terrified of the possibility of sociocide. I noticed today that countries who never recognized the regulations on genocide are referring to genocide. But what about ecocide? What about sociocide? And most of all, in the world of wisdom, what about cogitocide, cogitosphere, our ability to exercise what God gave us, not only to think, but also to exercise that wisdom that is essential to any long-term thinking. Medium and long-term thinking is not the case today. You will agree with, I think, many of you, but the case is very much short-termism and arbitrariness. The urgent need, I think, today, ladies and gentlemen, is to move away from the Anthropocene and towards a Humilocene. We could all benefit from a little bit of humility in addressing the challenges that we have to face. And in that context, the irreversible effects of climate change must be seen as an invitation for a fundamental rethink of our post-COVID world. Either we have a portal in which we are invited to step forward and transcend boundaries and civilities in the sense of building a step towards thought and praxis, or we have the unfortunate denouement of Baghdad or Damascus or Belgrade or Kiev and so on. So I think that there is no limit to creativity, and between string theory and cosmology, the idea of an infinite landscape of possible universes has as some have said, become not just acceptable, but taken for granted by a large number of physicists. Can we afford to take this for granted? And in this context, I would like to suggest we engage in systemic humiliation. Once again, ecocide and sociocide. We shred our relations with our habitat, with each other. We degrade our sociosphere and our cogitosphere, our sphere of thinking and reflection, to the point that we sacrifice our ecosphere and thus embark on our collective suicide as a species. 2030 is just around the corner, 2050 is not further. I won't be there to witness it, but I'm deeply concerned, as you all are. We are not important. What is important is our children and our children's children. So I would like to refer to some of the achievements here in Jordan, and that is maybe the next time we could meet in Petra. I think that we are probably, you're talking about quantum the next time. What about not only quantum mechanics, but quantum progress and development? What about the interdisciplinarity of all of this? I would like to thank the Scientific Society for active collaboration in an interdisciplinary ICPT, CERN, EASA, and ongoing materials. Physics research is where the RSS, the Royal Scientific Society of Jordan, which we founded in 1971, and I thank, of course, the University of Jordan and the University of Yarmouk for being initiators of the Petra School of Physics. Way to go. I think that we have another major challenge ahead. But once again, the MOU was signed with ICTP and Sesame on August the 1st, 2021. I thank you, Dr. Khalid Topan, for the purpose of promoting scientific research and education, training, and communication in Jordan, the Middle East, and North Africa. The MENA region is significant. It sets a framework in which to foster the development of the scientific capability of Jordanian and MENA scientists interested in working in synchrotron physics and applications by providing training scholarships to work with experts at the Sesame synchrotron in Alam, Jordan, and the Electra synchrotron in Trieste. This will be done with the goal of developing a pool of Sesame users within the Jordanian and MENA scientific community. MENA in Jordan we call WANA, West Asia, North Africa, because quite honestly, the no-name region is still the Levant, strangely enough. You have an Eastern Mediterranean Middle East region, as loosely described by Europe. You have the Gulf region for obvious reasons, but it is time that we recognize that 71 million people, at least Arabs, in terms of Lebanon, Palestine, Jordan, Iraq, and Syria, are the Levant region. If you were to add Turkey and Iran, and of course, if Israel would ever make its mind up about which region it wants to be a part of course, it is anything that it wants to be every time of the day. I've said to Israelis, you are simply too strong for your own happiness. So it's about time that you began to recognize the fact that the Visegrad region, Poland, Hungary, Czechia, Slovakia, 71 million people received 10 times the investment of the Marshall Plan. We in Jordan have not benefited from any regional thinking, although we are the most accommodating hosts of refugees and migrants. So in terms of the aim of collaboration in capacity building and climate modeling, obviously the 3 Gs that always come to my mind: geography, geophysics, and geopolitics, for that matter. Geography, geopolitics, geophysics, and geology. The 3 Gs are absolutely essential to understanding the effects of the Earth's warming and the discoveries related to the field of geology in general. And I won't go any further, but I'm hinting at the fact that Halford Mackinder, the great Roger Penrose would recognize Halford Mackinder as being the, in a way, the introduction to modern geography. And that was in 1908 when he said, the world's island, referring to the Arabian Peninsula, and he who dominates the world's island dominates Eastern Europe. I thought this was rather prophetic myself, because if you look at the strategic seismic line from the Baltic to the Black Sea to the Straits of Hormuz or to the Red Sea, you're talking about Eurasia, European, Asian. And I think that healing the rift in so many different aspects is benefiting from our determination enshrined in the International Year of Basic Sciences for Sustainable Development in 2022, IAEA, UNESCO, ICTP, Women in Science Initiative, and explorations of partnerships and resources for supporting large international research infrastructures such as Sesame. I'd also go on and say that the Soumaya University at RSS was granted associate member status of CERN's Compact Muon Solenoid CMS program. The membership allows Jordanian scientists, researchers, and emerging scholars to participate in CERN and CMS programs. So we have science for diplomacy, and this seems to bring in all the usual or unusual suspects. When it's science, there is no criticism of participating in looking for regional themes and how to further them. The SDGs have been given an almost a death blow. They have been unbalanced by COVID on the one side and war and conflict on the other. So we can't talk about food in isolation of water. We can't talk about nutrition in isolation from climate. We can't talk about children's health in isolation of all three. And the time has come to talk about an interdisciplinary approach. And in that context, I'd like to thank in particular the International Institute of Applied Systems Analysis, which is of which we are a prospective member as RSS as of 2019. And the prospective membership would mean championing the values of systems analysis as an approach to understanding and finding solutions to shared problems, both local and global. This integrated assessment approach reveals synergies, trade-offs, and feedbacks that can be harnessed to find co-benefits or avoided to stop unintended consequences. After all, much of the damage in today's world is the result of the laws of unintended consequences. I always remember the words of Sidney Bailey, the great Quaker anthropometrist, if I would describe him. Anthropologist leads to anthropometry, a metric for social development, in which he said, remember how wars end. We're very good at initiating wars, or very bad. Every 10 years I've lived a war in this part of the world. Every 10 years. And then we say, well, what about the consequences? Well, the consequences to human dignity are immense. And I would like to thank our researchers, particularly at RSS and elsewhere. The Light Metal Alloys Research Unit in the Advanced Research Center deals with understanding fundamental mechanisms of how solute atoms, vacancies, and defects interact inside metal alloys with different chemical compositions and under different thermal treatment profile to achieve high quality products in the automotive and aerospace industries. Can we become a hub for this region? Every international delegation visits on a binary basis the different capitals of the region, but there is no thought of how to stabilize the Levant. I think that this is an issue that we can all contribute to. The contribution to the understanding of those physics helps to enhance the production processes on a large industrial scale, not only to the quantity of products, was also to minimize the energy consumption along the process, which leads to minimizing the energy consumption and thus fewer greenhouse gases in the atmosphere. The output of the Light Metal Alloys Research Unit includes publication of its recent results in prestigious peer-reviewed journals such as Acta Materialia and Ultra Microscopy. And I would just like to say that in terms of publication in peer-reviewed publications is unfortunately should be a best step forward for Arab physicists, but I think you would all recognize that we are not doing enough in this field. So once again, I want to thank you all for responding so well to what we have in mind for you in terms of the active collaboration of our higher Council for Science and Technology, which is trying to act as a coordinator between our 20 plus universities, 30 plus universities, in focusing in terms of UNESCO. I have had conversations with the University of Kufa, with Baghdad, and of course UNESCO is playing a major role in terms of water. Blue Peace is one of the initiatives we'd like to share with you, and that is of course an initiative largely supported by the Swiss government and the Geneva Water Hub. So there is a lot out there which I don't have to enumerate, but I would like to suggest to you in lest we forget mode that our great scientists such as Ibn al-Haytham al-Biruni, Ibn al-Shatir, Muayyad al-Din al-Urdi, all of these names come to mind, as an enterprise cannot be built or based on individual countries. It is a contribution of Arab culture of which we are speaking here today. And I do remember Professor Sassoon from the Hebrew University saying to me, "Oh, I thank you so much for what you did for us in the 11th century." So I had to say, well, that was a bit before my time. But what are you doing for us in terms of intellectual generosity? And once again, I thank you for your intellectual generosity, and thank you for launching this event, which is nothing short of a big bang for all of us. I hope we'll see you soon and in person in Jordan and elsewhere around the globe. Thank you all, ladies and gentlemen, very much.
Thank you very much, Prince Hassan. And I think now we can move to Dr. Sandhu, the chair of the first session, because we have to go quickly to the program. We have very tight schedule. So Dr. Sandhu, the floor is yours. You are muted.
Unmute your mic, please. 1 minute, 1 minute. Okay, and now unmute, please, Dr. Sandhu.
Right. Yeah. Dear ladies and gentlemen, we are quite happy to be with you in this memorable day. And I would like to thank Prince Al-Hassan for his informative words and mentioned me. Thanks a lot, sir. In this first session, I am so proud to introduce to two of our great scientists, Prof. Takaaki Kajita and Sir Roger Penrose. Now we are going to start with Professor Takaaki Kajita. Prof. Kajita is the president of the Science Council of Japan. In 1998, his team found that when cosmic ray hit the Earth's atmosphere, the resulting neutrinos switched between two flavors before they reached the detector. This discovery helped prove the existence of neutrino oscillation, and that neutrino have mass. And in 2015, Prof. Kajita shared the Nobel Prize in Physics with Arthur MacDonald. Today, Prof. Kajita is with us, and he will give a talk about neutrino oscillation. Sir, Prof. Kajita, you are welcome with us, and the floor is yours now. Thank you very much.
Thank you very much for the kind introduction. And congratulations for establishing the Arab Physical Society. I hope that the Arab Physical Society will foster the research and education in physics in the Arab region. Congratulations. Now let me share my slide. Excuse me.
Yes.
Please slideshow.
Yes, I would like to. Okay. Yes. Okay. Today, well, sorry. Before moving on, I would like to. Sorry, too many things to do. Excuse me. Well, I'd like to switch off my own picture. Anyway, let me try. Okay, today I want to talk about neutrino oscillations. Well, now you see a photo in this slide, and this is the super Kamiokande detector. So I'm going to talk about neutrino oscillation experiments, and one of the experiments I'm going to talk here is the super Kamiokande. Okay, so this is the outline, and excuse me. Excuse me, I'm very sorry. I don't know what to do. Anyway, very sorry. I don't know how to turn off my own picture, my own video. Anyway, let me try. Okay.
What's the point?
Well, actually,
how can I help you?
The panels of people prevent me to see my own slide.
Now the slide is outlined now. What are neutrinos?
Yeah.
It's
yes,
okay.
yes. I know. I'm in this page, but I can only see a part of my page. This is a problem. Okay, maybe
you can stop. Yeah. Share it again, and don't use slideshow. Yeah.
Yeah, in fact, yeah, I give up to use this slideshow. So, I want to move on. Sorry.
Just click page by page.
Yeah, right. Oh. Okay, this is the outline. First, I have a brief introduction on neutrinos. Then I want to move on to the early days. Then I move on to the discovery of neutrino oscillations, solar neutrino oscillations, the third oscillation channel, future prospect, and summary. So let me talk about neutrinos very briefly. Neutrinos are fundamental particles like electrons and quarks. And neutrinos are something like electrons without electric charge. And in fact, this has a profound impact. They can easily pass through even the Earth, but they can interact with matter very rarely. Therefore, we are able to study neutrinos. And neutrinos have, like the other particles, three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And neutrinos have been assumed to have no mass. And finally, we can detect these neutrinos by, for example, by using a neutrino interaction with the nucleus. Then typically a charged particle is emitted. And this nucleus could be, say, water nucleus. Then in this case, this particle propagates in the water. And then this particle emits Cherenkov radiation. And therefore, we detect these Cherenkov photons. And by analyzing these photons, we analyze the neutrino event. So this way we study neutrinos. Now, I want to move on to the early days. Well, when I say early days, that means in the 1960s to 1980s, or maybe early 1990s. First, solar neutrinos. The sun generates energy by nuclear fusion processes. And during these processes, many neutrinos are generated. Therefore, if we are able to detect solar neutrinos, we can study the energy generation processes in the sun. Therefore, the detection of the solar neutrino is very important. In fact, more than 50 years ago, the pioneering Hooft experiment observed solar neutrinos for the first time. However, the observed event rate was only about 1/3 of the prediction. So this was known as the solar neutrino problem. People thought maybe there is something interesting in this result. Therefore, several experiments followed the initial result, initial experiment by Hooft solar neutrino experiment. And here I summarize the results from the subsequent experiments in the 80s and 90s. And here the horizontal axis is the threshold energy, and the vertical axis is the ratio to the standard solar model prediction. And all these experiments observed solar neutrinos, but observed flux was much lower than the flux theoretically predicted. So solar neutrino experiments in the 80s and 90s confirmed the deficit of solar neutrinos. But unfortunately, at that time, people were unable to understand understand why there was a deficit of solar neutrinos. Now, I want to switch to the proton decay experiments. Grand unified theories in the 70s predicted that protons should decay with the lifetime of about 10 to 30 years. Well, clearly, this prediction was extremely important. If one observes the proton decays, that means the unification of forces. Therefore, several proton decay experiments began in the early 80s. And here I show the list of the experiments in the 80s. KGF experiment in India, NUSEX in Europe, IMB in United States, Kamiokande in Japan, and Frejus in Europe. All these experiments wanted to observe proton decays. However, of course, in every experiment, there are backgrounds. And for these experiments, the most serious backgrounds are the neutrino interactions. And these neutrinos are created by cosmic ray interactions in the atmosphere. If a cosmic ray interacts with the air nucleus, typically a pion is created. And of course, pion is unstable. Therefore, pion decays to a muon. Muon is again unstable, therefore decay to an electron. During this decay chain, neutrinos are created. And some of these neutrinos interact in their detector, and they are the background to the search for proton decays. So the proton decay experiments in the 80s observed many atmospheric neutrino events. And because atmospheric neutrinos were the most serious background to the proton decay searches, it was necessary to understand atmospheric neutrino interactions. And during these studies, a significant deficit of atmospheric muon neutrino events was observed. Here, I summarize the results from Kamiokande and IMB experiments. Here, the horizontal axis is mu over E of the data over mu over E of the Monte Carlo prediction. Clearly, these two experiments observed a significant deficit in the muon neutrino interaction. However, unfortunately, these experiments were unable to find the reason for the deficit. Anyway, both solar neutrinos and atmospheric neutrinos show the deficit, and people thought maybe the deficits were due to neutrino oscillations. And of course, neutrino oscillations were predicted more than 50 years ago, theoretically by Maki, Nakagawa, Sakata, and independently Pontecorvo. According to them, if neutrinos have mass, neutrinos change their type or flavor from one type to the other. For example, mu neutrino could oscillate to tau neutrinos, and let's assume that mu neutrino is created at this point and start to propagate to the right. Then at some point, the probability that mu neutrino to remain mu neutrino goes down. But if they continue to propagate, this probability come back to unity. If they propagate further, then the probability goes down, goes up, or goes down, and so on. And when mu neutrino disappeared, tau neutrino is appearing. So this is the neutrino oscillations. Therefore, if this is happening, for example, in the atmospheric neutrinos, then one can naturally explain the deficit of muon neutrinos. Therefore, people have been thinking that neutrino oscillations could be the cause for the atmospheric muon neutrino deficit. Furthermore, the small neutrino mass might be a way to study physics at very high energy scale. Well, this is called the Sisson mechanism. Therefore, people thought the observation of the small neutrino mass is very important. Now, I want to move on to the discovery of neutrino oscillations. Well, the detector that discovered neutrino oscillation was Super Kamiokande. And Super Kamiokande is a very large water Cherenkov detector. It is a 50,000 ton water detector. It has about 40 meters in diameter and 40 meters in height. And it is located about 1 kilometer deep underground. And by the way, this is an international collaboration. At present, we have about 200 collaborators from 10 countries. And I just want to show you one slide, one photo. This is the photo of the Super Kamiokande. And this photo was taken in January '96, when we essentially finished the construction of the Super Kamiokande detector. And at that time, we were in the middle of the filling the detector with pure water. Anyway, the experiment started from April '96. And here I'd like to show you one example neutrino interaction in Super Kamiokande. This is a typical mu neutrino interaction. You can clearly see a single Cherenkov ring, which is produced by a charge, by muon. And Super Kamiokande observes about 10 neutrino events per day. And therefore, we analyze these neutrino events and try to understand what's going on with atmospheric neutrinos. Now, I'd like to discuss what we thought when we started the analysis in Super Kamiokande. As I said, these neutrinos are created by cosmic ray interactions in the atmosphere. Therefore, some of the neutrinos are created above the Super Kamiokande detector, maybe 10 to 20 kilometers above the detector. And these neutrinos come to the detector after traveling 10 to 20 kilometers. So maybe these neutrinos do not travel long distances, therefore they may have no time to oscillate. Yeah. On the other hand, neutrinos are also created in the other side of the Earth. And these neutrinos have to travel long distances before reaching to the Super Kamiokande detector. Since the flight length is really very long, typically 10,000 kilometers, therefore, these neutrinos may have enough time to oscillate. So if we think this way, then we can easily expect that for downgoing neutrinos, we may not see the effect of neutrino oscillations. On the other hand, for upward-going neutrinos, we may see a really oscillation effect. And as a result, we may see a significant deficit of upward-going neutrinos. Well, this is simple. However, the point is statistics. We really needed a large detector, and therefore we really needed Super Kamiokande. Anyway, in 2 years of the Super Kamiokande data analysis, we were able to report the first important result at the neutrino conference in 1998. And here I copied one of the slides we presented at the conference. And in this slide, we showed the zenith angle distribution for electrons and muons. And for muons, by the way, cosine theta means cosine zenith angle, and 1 means downgoing neutrinos, and -1 means upward-going neutrinos. And clearly, for downgoing neutrinos, the data and expectation agreed quite well. On the other hand, for upward-going neutrinos, the data showed almost a factor of 2 deficit compared with the expectation. This can be easily interpreted. This can be easily explained if we assume neutrino oscillations, as shown here. So this way, Super Kamiokande discovered neutrino oscillations. Since then, many experiments have been studying neutrino oscillations, mu-neutrino oscillations. Here is the list of the experiments that studied neutrino oscillations. And some of them are atom-spec neutrino experiments, and some of them are long baseline, accelerator-based long baseline experiments. And in particular, I'd like to show you the progress of these experiments, accelerator-based experiments. The first accelerator-based experiment was the K2K experiment. That was the long baseline experiment between KK and Super Kamiokande. And this is the result from K2K. And clearly, they saw an energy-dependent deficit of muon neutrinos. And this way, K2K confirmed the oscillations. The second one is the MINOS experiment in United States. MINOS has much higher statistics. And well, if you look at this graph, you can see the energy-dependent deficit of muon neutrinos is much more clearly observed. And the current generation experiments are T2K and NOVA. And in these experiments, they tune the beam energy so that the maximum oscillation effect can be observed. And in fact, in these experiments, they observed a really significant deficit of muon neutrinos. And by analyzing this data, they can precisely determine the mixing parameter and delta M square. Well, in the previous page, I showed the deficit of muon neutrinos in accelerator-based long baseline experiments. However, all these were muon neutrino deficit. And if the oscillation is muon neutrino to tau neutrinos, one should observe the appearance of tau neutrinos. And this was achieved by the OPERA experiment. This was one of the tau neutrino candidates in OPERA. So they observed 5 tau neutrino candidates, and expected background was only 0.25. So they observed the appearance of tau neutrinos. So this way, they confirm mu to nu tau oscillations. Also, Super Kamiokande and IceCube statistically confirmed the appearance of tau neutrinos. Now, I'd like to move on to the solar neutrino oscillations. Well, the key experiment to confirm the solar neutrino oscillation was the SNO experiment. SNO is a 1 kiloton heavy water detector. It was located 2 kilometers very deep underground. And here I'd like to show you a photo of the snow construction. So in order to construct the detector, 1 million pieces of the detector were transported using the mine cage and assembled in the very clean environment in underground. And finally, they filled pure and heavy water in 1999. And this is one of the main results from snow. And by using the heavy water, they were able to observe both charged current and neutral current interactions. Of course, charged current interactions are only sensitive to nu E flux. On the other hand, neutral current interactions are, of course, sensitive to all the flux. And therefore, both charged current and neutral current observations constrain the flux of nu E and nu mu plus nu tau flux. The constraint from charged current is here. The charged current only constrains the nu E flux, of course. The constraint on the neutral current, constraint by the neutral current measurement is here. And clearly, you can see the intersect is here, which shows non-zero nu mu plus nu tau flux. And by the way, furthermore, there are two other bands. They came from the elastic scattering measurements by Snow and Super K. And these constraints are also consistent with the other two with the other constraints. Therefore, this was the evidence for the finite nu mu plus nu tau flux. And therefore, the data were just consistent with solar and neutrino oscillations. However, of course, this was just the evidence for the finite nu mu plus nu tau flux. There have been several other possibilities discussed in the community. Therefore, I'd like to mention another experiment, that is the Kamran experiment. Kamran is a 1 kiloton liquid scintillator detector located in Kamioka here. And this experiment started in the early 21st century. And around that time, there was many nuclear reactors in Japan. And therefore, the Kamran experiment was able to observe neutrinos created by these nuclear reactors. And furthermore, many reactors are located at a distance of about 180 kilometers. Therefore, this is a kind of long baseline reactor experiment. And the result is shown here. The horizontal line is, horizontal axis is L over E, and the vertical axis is the survival probability. And you can see the deficit, recovery, and so on. And this is really consistent with neutrino oscillations. And with this measurement, people were really convinced that solar neutrino deficit was indeed due to neutrino oscillations. Finally, before finishing the solar neutrino oscillations, I'd like to mention the recent results from Brexino. This is a sub-MeV solar neutrino detector. The Snow and Super K were only sensitive to the high energy part of the solar neutrinos, boron-H solar neutrinos. And according to the matter effect, MSW effect, the survival probability of solar neutrinos should be like this pink line, pink curve. Therefore, we really wanted to observe the sub-MeV solar neutrinos and confirm this MSW prediction. In fact, the Brexino data were really consistent with the MSW prediction. Finally, I just want to mention that Brexino reported the detection of the CNO neutrinos recently. This is another breakthrough in the solar neutrino detection. Now, I'd like to move on to the third oscillation channel. Well, since there are 3 neutrinos, there should be 3 mixing angles, and therefore there should be the third oscillation channel. And therefore, after the discovery of the solar neutrino oscillations, the community's interest was the discovery of the third oscillation channel. And the third oscillation channel was indeed discovered very clearly about 10 years ago. And here I list the experiments that contributed to the discovery of the third oscillation channel. So clearly the basic structure for 3-flavor neutrino oscillation has been understood. So therefore, I think we had a great achievement. And here I plot the allowed oscillation parameter regions. There are 3 mixing angles shown in the bottom panels. And also there are 2 delta M squares and CP phase. So clearly, by now, many of the mixing parameters and delta M square parameters have been determined rather precisely. Furthermore, the current experiment begin to constrain the CP phase delta. By the way, I should mention that blue curves show the normal mass ordering, this one, and the red one shows the inverted mass ordering. So current experiment begin to favor normal mass ordering. Okay, now I'd like to move on to the future prospect. Well, this is the agenda for the future neutrino oscillation experiment, neutrino experiments. First of all, we'd like to know the neutrino mass ordering. Namely, we'd like to know nu3 is the heaviest or the lightest. As I mentioned in the previous slide, the present data slightly disfavor the inverted mass ordering. Also, we'd like to know if CP is violated in the neutrino sector. We think this is quite important because CP violation in the neutrino sector might be related to the baryon asymmetry of the universe. Furthermore, we'd like to know the absolute neutrino mass. Neutrino oscillation experiments are only sensitive to the mass difference. Therefore, we need independent measurement on the absolute neutrino mass. Also, we'd like to know if there are structures beyond the 3-flavor framework. Namely, we'd like to know if stellar neutrinos exist. And finally, we'd like to know if neutrinos are Majorana particles. And well, certainly, therefore, double beta decay experiments are very important. And from now on, I'd like to essentially concentrate on the CP violation. And we'd like to observe if oscillation of neutrinos and those of antineutrinos are different. If we observe the difference, it will be the first step to understand the origin of the matter in the universe. So there are 2 large projects going on. One is the Dune experiment in United States, well, located in United States. Another is the hypercamiogan project located in Japan. as I discuss in the next page, dune and hyper-K have similar sensitivities, although the experimental details are largely different. And therefore, we'd like to see the consistent results from these two complementary experiments. And here I show the sensitivity from dune and hyper-K about the CP violation. So if the CP phase is in the most lucky case, then both dune and hyper-K should observe about H sigma effect. So clearly, both experiments have very high sensitivities. However, as I mentioned, if we look at the details of these experiments, there are many differences. Dune is really a very long baseline experiment, 1,300 kilometer baseline, and therefore dune has a large matter effect. And in fact, large matter effect is very good for the determination of the mass ordering. On the other hand, hyper-K has only 300 kilometer baseline, therefore the matter effect is small. The beam energy is high in case of dune, and hyper-K uses sub-GeV beam. The detector technology is of course different. Dune is a liquid argon TPC, hyper-K is water Cherenkov. So clearly, there are many differences, and we'd like to be convinced DCP violation by the consistent results from these two experiments. Now, from now on, since I'm slightly involved in hyper-K, therefore I'd like to essentially focus on hyper-K. First of all, this is the history of the water Cherenkov detectors. The first generation was the Kamiokande and IMB, and these experiments really had a significant result. The present generation is super-K, and super-K also had discovered neutrino oscillations and used as the far detector for long baseline experiments. So clearly, these histories suggest that water Cherenkov detector can be a natural extension of the present super-K detector. And here I'd like to show you the status and plan. Hyper-K is really going to be a very large water Cherenkov detector. It will be about 70 meters in diameter and 70 meters in height. And the project was approved 2 years ago, and already the construction is going on. This is the photo of the access tunnel. Actually, the excavation of the access tunnel was completed in February this year. And the experiment will start in 2027. And with this extremely large detector mass, we expect many important research topics in neutrino physics and astrophysics and the search for proton decays. By the way, of course, for this kind of large project, we should work together with the international community. Hyper-Kamiokande is really going to be a very large international collaboration. At present, Hyper-K has about 500 members from 20 countries, and these numbers are still growing. Now, I'd like to show you 2 examples in the hyper-K physics. Now, one of the physics is the solar neutrino detection. And here, I summarize a slightly old oscillation parameters. And in the community, there was a well-known tension between the delta M square determined by Kamran and delta M square determined by solar neutrino experiments. Now, depending on the delta M square, the solar neutrino flux could be different between daytime and nighttime. Therefore, one of the important measurements could be the observation of the day-night effect. And because of the extremely high statistics in hyperkamiokande, even if the expected day-night effect is rather small, hyper-K should be able to observe statistically significant day-night effect. If the delta M square is high, then hyper-K should be able to observe a 4 sigma effect after 10 years of operation. Or if delta M square is low, then the statistical significance could be 8 sigma. So clearly, this way, day-night effect could be a way to tell us the true delta M square in a completely independent way. And finally, before finishing this talk, I want to mention the proton decay searches. Because of the huge mass of the detector, the next generation experiment should be sensitive to the proton decays. If proton mainly decays to E plus pi 0, then say after 20 years of the operation, hyper-K should be able to find 3 sigma evidence if the true proton lifetime is shorter than 10 to 35 years. On the other hand, if the main decay mode is neutrino plus K plus, then we expect that Dune could have a slightly higher sensitivity. Anyway, I think we should be serious in searching for proton decays. And here I show the one of the key plots. Invariant proton mass versus the total momentum for the background events. For the signal events and for the background events. And you see in water, there's a free proton. And the delta M, total momentum and the invariant mass from free proton decay is here. And the proton decays in oxygen are shown by these blue dots. Clearly, free proton decays have a very distinct signature. And if we look at the background, you see, even for 10 to 35 years, we may not have significant background by atmospheric neutrinos. So in order to reach 10 to 35 years, free proton decays from hydrogen is very important. Okay, let me summarize. Proton decay experiments in the 80s observed many contained atmospheric neutrino events and discovered the atmospheric mu-neutrino deficit. Subsequently, in 1998, superkamiokande discovered neutrino oscillations. Solar neutrino experiments began in the 60s. Various solar neutrino experiments before year 2000 observed the deficit of solar neutrinos. The SNOW experiment discovered solar neutrino oscillations by the measurement of charge current and neutral current reactions of solar neutrinos. And since then, various experiments have studied neutrino oscillations. And through these studies, this 3-flavor oscillation structure has been understood. And we think that the neutrino physics will continue to be very interesting. And I hope that more and more colleagues in the Arab Physical Society join the neutrino studies. And finally, I'd like to repeat congratulations for the establishment of the Arab Physical Society. That's all from me.
Thank you very much, Professor Kajita. It is quite very, very interesting subject, and we get it from the direct source. It's not from textbook, not from the advanced book. Thanks a lot for that information. And now it's the time for the questions. I saw here some questions for you, sir. Let me see. Oh, it's quite long questions, but I try to find something small because we don't have enough time to read and to answer. This questions is from Sonia Haddad. It is, what will be the signature of major character to neutrinos?
Okay, thank you very much. If neutrinos are Majorana particles, then we expect a particular double beta decay, that is neutrino-less double beta decay.
Yeah.
So we really want to observe neutrino-less double beta decay.
Okay. This is a long question from Mr. Abdusalam Hamouda. At the end of the years 80s and during 90s, it was observed some indications for neutrinos oscillation near reactors. Now, based on the neutrinos reactors, normally some experiments are looking for sterile neutrino. What do you think about sterile neutrinos and their effect on long baseline experiment as atmospheric neutrino experiment?
Okay, thank you very much for this question. Well, first of all, the sterile neutrinos are not established yet. Therefore, the first important thing is to continue the research on the sterile neutrinos or sterile neutrino oscillations by various ways, including the nuclear reactors. And certainly, if we observe definite evidence for sterile neutrinos, that would be really exciting. But to be honest, I think we are far from the evidence. We still have many high quality data to be convinced the existence of sterile neutrinos. By the way, atmospheric neutrinos are not very sensitive to sterile neutrinos.
Okay, thank you. I think this is the last question. It is long as well. It is from Tamer Tulba. Thanks, Prof. Takika, for this comprehensive overview on the neutrino oscillation topics. Now, as we are going to a very exciting time with the latest result from T2K on the delta CP, which might be finally revealed in the next decade or so. The next generation experiment will seek precision measurements. How do you see the possibility to benefit from the Arab desert to build a neutrino experiment that may host a next generation long baseline experiment? How we should plan for this scientifically and politically?
Oh, thank you very much. In fact, today I focused on neutrino oscillation experiments, but in the field of neutrino physics, there are many research topics, including the double beta decay. Therefore, I think you have to think very seriously what to do next.
Mm-hmm.
There are, in fact, many experiments that contributed to the development of neutrino physics. And therefore, I would like to encourage you to join to the neutrino research.
Okay. Why in double beta there are no neutrino, and in the higher energies we have neutrinos? Do we know physics behind that?
Oh, okay, thank you. Well, if neutrinos are Majorana particles, then well, the image is like this. A neutrino produced by a beta decay can be absorbed by, well, okay, maybe it will be easier for me to show the oh, okay, well, okay, let me say, in double beta decay, two beta decays are created at the same time. And therefore, in principle, two neutrinos are created in the same time. But if they have mass, they can be converted to the say, antineutrinos. Therefore, it can be interpreted as an absorption of the neutrino. Therefore, as a result, there should be no neutrinos in the final stage.
Okay. Okay. Another question, it is quite interesting, from Salah Unhama. He asked something interesting. Actually, it was in my mind. Is there any experiment of neutrino and Higgs boson interaction? You know, the Higgs boson is related to the mass, and the main concept of the oscillation of the neutrino, it has a mass. And so what is the relation between these two concepts?
I see. Well, typically, well, first of all, experiment is as far as the experiment is concerned, I have no idea about the neutrino Higgs boson interaction experiment. I have really no idea.
Yeah, I know that. Okay. Mm-hmm. I think.
Sorry, maybe I would interrupt you here. What would be the interpretation of the masses that the neutrino have? Neutrinos in your explanation. I mean, the main goal is yeah. Go ahead.
Yeah. Okay. Thank you. Since the neutrino mass is really extremely small,
Yeah.
say compared with the mass of quarks and charged leptons, the neutrino mass is smaller by, say, 10 orders of magnitude or even more. Therefore, typically people are thinking that the neutrino mass was generated by other mechanism, and people call this mechanism as seesaw mechanism. And in the seesaw mechanism, the high energy physics is related.
Yeah, here there is a note from Mohammed Mondi. He said solar neutrinos come directly from the sun. They are not a part of cosmic ray neutrinos.
That's right.
Okay, I found this on the web for he said solar neutrinos come directly from the sun.
Well, certainly we observe neutrinos directly coming from the sun.
Yeah.
Also, independently, we observe neutrinos created by cosmic ray interactions.
Okay. Okay, I think we cover now. Do you think that the discovery of marginal fermions is condensed matter will help to observe Majorana particles in HEP?
Thank you. I'm very sorry. I don't have the answer to this question. I'm very sorry.
Okay, thank you very much, sir. And we were quite happy with your talk, and it is quite useful for all of us. Thanks a lot. Thank you very much.
Thank you very much for listening.
Now I am so proud to introduce you Sir Roger Penrose. Actually, I met Sir Roger Penrose about 5 years ago. Sir Penrose is an emeritus Rose Bowl Professor of Mathematics at the University of Oxford and in other colleges. Sir Penrose has received several prizes and awards, including the 1988 Wolf Prize in Physics, which he shared with Stephen Hawking for the Penrose-Hawking singularity theorems, and one half of the 2020 Nobel Prize in Physics for the discovery that black hole information is a robust production of the general theory of relativity. Fortunately, and we are quite happy to say that Sir Roger Penrose, he is with us today, and he will give us a talk about black hole singularities to cyclic cosmology. Sir Penrose, you are welcome with us, and the floor is yours now. Thank you.
Thank you very much. I hope you can hear me.
Yes, I hear you.
Good. And I hope you will be able to see the pictures I want to show.
Yeah.
Excuse me. It's a great honor for me to be able to address the Arab Physical Society. I certainly hope I can do it justice.
Thank you.
I want to talk about black hole singularities and cyclic cosmology. The Nobel Prize, the 2020 Nobel Prize for Physics was awarded, well, the citation was that the black holes were a robust prediction of general relativity.
Yeah.
I would like to correct that slightly, because what I did was to show that singularities are a robust prediction of general relativity. I mean, no, this is, you correctly quoted what they said. I just want to clarify it a little bit, because this is the existence of singularities.
Sorry, the screen is not shared.
Oh, can you see the, I'm only showing you the can you see anything in the screen?
Would you please share it?
I did, but I hope,
Not yet.
can you see the, it's just the title. Can you see the title?
No.
No. We have to arrange that. How do we do that?
No,
Do it
go
again.
to share screen. It's downstairs. Click on share screen.
Oh, well, it's, I thought I was sharing screen.
No. As before, we did it before half an hour. You remember that?
Well, it must have disappeared for some reason. How do I do it? Because I don't see anything on my picture here which would allow me to do that. Do I have to close it down?
Just please open the PowerPoint presentation in your desktop and click on share screen.
The whole thing is open, but I see nothing like that at the moment. I think I have to close it before I can see anything. I have to warn you that I'm no good at these things. I don't see anything apart from my pictures. Now, how do I see something else? Wait a minute, maybe I can find something.
Just minimize the zoom first. You will see your desktop. Then click on your PowerPoint presentation.
I'm afraid I don't. All I see is my presentation. I don't see anything else.
Switch it off, close it first.
I have to switch it off, I suppose. After all this time, let me just try and switch it off. Is it the red thing at the top?
Nothing.
I'm not
shared.
Sorry?
It's not shared.
There's a green button, share screen, green button.
There isn't in what I see, unfortunately, because it's not, I can only see the presentation, you see.
Yeah, now close it. Close the presentation first.
How do I close it?
Go to the corners. There's small dash or X and click.
An X?
Yeah, there's X, click it.
Okay,
click on X at the corner.
I've clicked on X.
Or press Alt plus S.
Now what?
Keyboard, Alt plus S.
Out?
Yep.
It is at the top of the screen. Home. Insert. No, not all that stuff. What is it? PowerPoint. Or share screen at the bottom. See if I can find it. No, I see. Ah, now I can see it. Yes. Now share screen. How is that? Anything useful?
Yeah, right now share screen. The bottom, green button down. Share screen.
I did the green button.
Yep. And click again to the presentation from that.
I have to find the right one, which is always tricky because they'll show me so many things and I never know which the right one is. Yes, that could be it.
We did it.
I know.
A while ago, 60 minutes ago. Yeah, we did it. Easy.
I can do share screen again. Is that any use?
Yep.
Now what? I have to find the right presentation. It's this one.
Yep.
Yeah.
Excellent.
Yeah.
Now you see it. Will you see it?
Yes, yes. Black hole singularities to cyclic cosmology.
Yeah.
Okay, well, I'll try and see if this works.
Yeah.
I see the whole picture. Yes, okay.
No, it's okay. It's okay. Just go slide by slide.
Right. Well, I wanted to talk about the Nobel Prize, which was for the robust prediction of black holes. But technically speaking, it was for the robust prediction that singularities occur. It's still, I believe, not even proved now that necessarily the singularities which are not inside black holes are unstable. There is a thing which I call cosmic censorship, which would assert that the singularities, the stable singularities, are necessarily in black holes. I think it's still unproved. But let me forget about that and assume the natural assumption, which is if there are singularities, that they are necessarily hidden in black holes. And the picture, this was the picture from my paper, and I just wanted to say a little bit about it. Time is going up the picture, and we see, of course, I have to throw away one dimension in order to represent it. This is a spherically symmetrical collapse, which in 1939, Oppenheimer and Snyder showed that if you had a collapsing dust cloud, this would, and it was spherically symmetrical, this would necessarily focus inwards towards a singular point where densities go infinite. It's not so surprising because dust means no pressure. And secondly, more importantly, spherical symmetry means everything is focused to a central point. So it's not so surprising that you get a singularity in these situations. But what I was able to show was that in the generic situation, when you introduce perturbations to this model, the picture I have in the paper, which I just show you here, is in fact assuming the spherical symmetry. And you can see that the matter falls inwards, and you have the singularity in the center here. Now, if you imagine irregularities, and there was a sort of belief, largely because of a paper published by Lifshitz and Khalatnikov, two Russians, who seemed to show that in the generic situation, you would not get singularities. So the picture was that the material would collapse inwards, something very complicated would go on, swirl around, and then come swishing out again. And I think this was a common view that people had. I had a look at the paper by Lifshitz and Khalatnikov, and I was not convinced that their methods would be robust. In fact, there was an error in the paper. I didn't see the error. I think it was found later by Belinsky in collaboration with the other two, and they did find the error in the paper. But not knowing about that, I thought independently about generic collapse. And for this, you need a criterion which is not disturbed by perturbing the initial state. So in this, I had to imagine, you see this little ring in the middle, you have to add another dimension, so that little ring is a spherical surface. And the peculiarity of it is that if you imagine a flash of light on that ring or that sphere, which I call a trapped surface, the flash of light inwards will be reducing in its area, but the flash of light outwards will also be reducing in its area. And this is unusual. This is what I call a trapped surface. And I was able to look at such a thing. You can perturb it and you will not remove that condition. And you can show that this thing will, well, by looking at techniques, which I'll just briefly indicate, not very much, but I hope I can move things forward by, perhaps that does it, yes. First of all, we have light cones. This is a crucial picture, part of the picture. At every point, you have the null cone, which represents signals have to travel on or within the future cone. And that's the way things are propagated in general relativity. Now let's move to the next picture. You have these null cones in general all over the place. And in the black hole picture, you imagine the future of this region. That's what I was really considering. You look at the trapped surface and you look at its future. That's the shaded region. And then you look at the boundary of this future. And there's various things you can prove about boundaries of futures. And the thing is that they actually behave quite nicely. If you look at the boundary, you will imagine horrible things like caustics and crossing regions take place. And so you might say, well, how can you say anything about what goes on? But what is nice about the boundary of the future is that these rays, which are null rays, lie on the boundary. And when they start to cross over, they don't remain on the boundary. So you stop them off and you have a nice surface. I won't go into the details of the argument here, but just to give you a general picture. So one thing was the focusing, well, that the boundary of the future was generated by light rays. The second point is you have to look at the kinds of curvature that are present. And the different kinds of curvature are nicely illustrated by the most early observation, direct observation of general relativity, which was in particular the Eddington expedition, which looked for eclipse of the sun, and you could then see the stars, and the stars were displaced outwards because of the focusing effect on light rays. Now, there are two effects you can see here at once. One is the effect of the sun. If you imagine the sun was transparent completely and that without any refractive index, that the light rays would be focused by the inward, well, let me push to the next picture, I think makes this clearer. I hope I can go backwards when I need to. If you look backwards along light cone, you see the Ricci curvature. The curvature splits nicely into two parts. One is the Ricci part, and the other is the Weil part. The Ricci part, according to Einstein's equations, is the source of gravity. The Weil part is the free gravitational field. So people didn't tend to think of it this way, but it's really a nice way of thinking about it. It's a bit like with Maxwell's equations. You have the source, which is the charge current vector, and you have the field, which is the Maxwell field. In general relativity, they occur at the same order of derivative, but you see that the source is the Ricci tensor and the field is the Weil tensor. And it's very useful to think of that separation, 10 components each. Now, the Ricci curvature focuses, as we see in this previous picture, the focusing is like a positive lens. So the sun behaves like a positive lens, which magnifies, and that pushes the image. That is to say, things which were further in are pushed further outwards. It looks like a magnification. So that the outside the sun's image, you see that the images are pushed outwards, and that is the direct form of the Ricci curvature, the positive lens of the sun. And secondly, you see that the pushing outwards gets less in the radial direction, and it goes out in the angular direction. So you see that a circular pattern will get distorted into an ellipse pattern. And this is the effect of the Weyl curvature. So the Weyl curvature is like an astigmatic lens. It changes circular features into elliptical features, whereas the Ricci curvature simply magnifies. So that's a useful way of thinking about things. And we have the effect that if you have lots of, say, oscillating Weyl curvature, it behaves like Ricci tensor. You have a sort of residual effect, which is really the energy in the energy in the matter gives you positive focusing. The energy in the gravitational wave comes from, if you like, oscillation between astigmatism in one direction and then the other direction, and you have a correction term which gives you a focusing. So the focusing is always inwards, and it is this fact which enables you to show that when you start with the rays focusing inwards, they will continue to focus inwards, and that's why you have this trapped surface, which I was describing. Let me go back to the picture we had a minute ago. The boundary of the future necessarily reduces in its area, and therefore you get this thing focusing inwards, and you get a compact surface, and this compact surface leads you to a contradiction to the evolution from a non-compact initial surface. I won't go into the details of that. My argument was a bit clumsy at one point there, and Charles Misner was able to produce a much neater argument. And I think the way to state this theorem is much using his method to show the contradiction between the initial non-compact surface and the compact boundary to the future of the to the trapped surface. I don't want to go into the details any further than that, except now let us talk about you see, when I gave a talk about this in King's College London in 1964, according to the movie, Stephen Hawking was there and with sparks coming out of his head or something, being inspired by the talk. In fact, he was not present at that lecture. However, Dennis Sharma, who was at Cambridge at the time, heard about my talk, and I did give a repeat in Cambridge. And then I talked about the details of the argument to Stephen Hawking. And then he, I think George Ellis was present in a private discussion that I had with the two of them afterwards. And they developed the arguments to apply, or particularly Stephen Hawking, to apply to cosmology. So here we have the picture. Well, you imagine the Big Bang at the bottom, time is going up the picture. I've also introduced the cosmic expansion that we see due to, well, people call it dark energy. I think it's perfectly consistent with the cosmological term in the Einstein equations, which mean a positive cosmological constant. And whatever it is that's causing the exponential expansion seems to be completely explained by the positive cosmological constant introduced by Einstein for the wrong reason. He wanted a static universe, and then he tried to retract his positive cosmological constant. But fortunately, once it was in there, people were taking it seriously, and it is the best explanation for this exponential expansion. That's not the point I want to make particularly here. You may see at the back something complicated going on. That's just because it's hard to draw an open universe, and I was assuming that it might be open spatially or it might be closed spatially. That's not relevant to the arguments I want to use. It could be either way, but if it's open, you could imagine the thing just keeps on going at the back or not. Doesn't matter in the pictures. Now, roughly speaking, what Stephen was able to show using the techniques, and then we got together afterwards. He had 3 papers in the Royal Society, and we got together afterwards for the 4th paper to show from very general considerations, you can't get rid of this initial singularity by perturbing it. Now, there is a great problem about this. You see, people would tend to think that the collapse, gravitational collapse, is basically the time reverse of the Big Bang. And so here we have, imagine of a collapsing universe, and this is the sort of picture, the time reverse. But if you imagine irregularities in this picture, it will not look very much like the Big Bang at all. You'll have complications, irregularities, which will cause black holes, and these black holes will congeal. And instead of having a nice picture like this, you will have a very complicated collapse, which I've drawn schematically like this, with lots and lots of black hole singularities. These will congeal, and you'll have an incredible mess. Instead of the Weyl curvature becoming very small, I should explain that the Weyl curvature in the Big Bang seems to be very small. In the remote future, you will get a very, very irregular situation like this. And this will be by far the commonest situation. And it seemed to me a great puzzle why you did not get anything like this in the Big Bang, a very complicated initial state, which would be nothing like what we actually see. And I remember having a talk to Jim Peebles at one point, way back in around about the turn of the century. And I raised the issue, why did cosmologists not consider these complicated situations? And there are many examples of very, very complicated situations which are known, and most of them which are not known. And he said, well, because the universe is not like that. And I presume he was basing his statement on the uniformity of the cosmic microwave background. And so this, to me, was a great revelation, because it said, well, these are not these very, very complicated solutions, whereas these are generically to be expected by a very, very large probability. I mean, you can work out the entropy and therefore of the black hole using the Bekenstein-Hawking formula, and you can see the entropy in black holes is enormous, and therefore in the reverse time, you have an extremely large entropy possibility. And why do you not see in the initial state these very, very complicated situations? And so it seemed to me a great puzzle. Let's continue with this. Sorry, I'm going the wrong way. Of course, one of the explanations people tend to produce is that somehow you have to consider inflation. And here I have a magnifying glass to try and see what inflation looks like. And the argument is that you have something like an exponential expansion in the very, very early universe. But that does not solve the problem, because why was that not present in the future situation as well? You could introduce the inflaton field, and it makes virtually no difference to this picture whatsoever. So it does not get around the problem of the very peculiar initial state of the universe. Now, there's another feature that I want to point out here. This is the very early COBE satellite, and they made this remarkable observation of the microwave background. And this graph, which I show you here, very famous graph, you can see the microwave background, the intensity is up the picture, and to the right, we see the frequency, and the curve that you see in the microwave background is very, very close to a Planck curve. In fact, it's extraordinarily close. You see the error bars, which are here, are magnified by a factor of 500. So even the worst case is really down here. If you reduce it by a factor of 500, the errors are way, way, way within the thickness of the incline. You have the most perfect Planck curve which is ever seen in physics, as I understand it. And this is telling you, what's it telling you? Well, you're telling you what you're looking at with matter and radiation in thermal equilibrium. What does that mean? Maximum entropy. And it struck me as a big paradox, because you're looking at the very earliest thing in the universe, the very earliest thing you see. Well, the entropy in the universe should be going up. So therefore, if you go backwards in time, the entropy should be coming down, down and down and down and down. And the earliest thing you see is a maximum. That struck me as very, very odd. Of course, the universe is expanding, so you might worry that that's a condition, but it's not the answer. You can see quite easily it's not the answer. And let me not go into that, but it's clearly not the answer. The answer is, not an answer really, but the fact is that what we are seeing is indeed maximum entropy with regard to the radiation and the matter, electromagnetic radiation and matter in more or less in thermal equilibrium. So let's move forward and see what this is really telling us. In these pictures, I'm going from left to right. The top three, you imagine a gas or something in a box, and you started off with in a smaller box, constrained to be in one corner like that. You open the box and it spreads out. Entropy increasing from left to right, time increasing from left to right, and uniformity increasing from left to right. So this is the sort of thing you tend to expect for systems. However, with gravity, suppose you imagine have a galactic scale box with a lot of stars running around, and now entropy increasing from left to right, time increasing from left to right, you have a very opposite looking picture. Uniformity isn't very low entropy. What is high entropy is the black holes. And in fact, it's enormously high. When you consider the Bekenstein-Hawking formula, you see the entropy goes shooting up enormously when you find black holes. So what you see is this curious combination between radiation, top left, radiation and matter, I mean electromagnetic radiation and matter in equilibrium, and that is spread out uniformly, and the gravitational degrees of freedom are not activated. So you have top right, bottom left, uniformity. But that means that the gravitational degrees of freedom were for some reason constrained to be low. And this is a real puzzle. Why should it be constrained to be low? An act of God or what have you? Well, we're trying to do physics, so we don't want to talk about it in those terms. I should mention this point, which was made by Schrödinger, which is very relevant to all these considerations. Here we have, how do we make use of the low entropy? Well, what do we make use of? The sun, you see. What does the sun do, which creates life on Earth and all sorts of things? People say we get energy from the sun, but Schrödinger was pointing out, no, that's wrong, because the energy from the sun more or less all goes away. Of course, there's global warming, we mean it doesn't quite all go away, but the major effect is that during the day it comes in from the sun, during the night it goes back out again. So we don't get energy from the sun, basically. What we get is the contrast between the sun, which is a hot spot in a dark sky. So it's the contrast between the hot spot and the dark sky. The hot spot means that you have, relatively speaking, high frequency photons, and in the dark sky, relatively speaking, low frequency photons going away. So you need many, many more photons to carry the same amount of energy to go out as comes in from the sun. So the main point is that the sun is a hot spot in a dark sky, and you use the fact that the energy is spread out into many, many more degrees of freedom when it goes out. And this is what the plants live off, and we live off the plants. And so we don't benefit from the sun being out there, being a hot spot. It's the contrast between the hot spot in the sun and the dark sky. If the sky with the temperature of the sun all the way around, it would be no use to us whatsoever. So we're benefiting from the imbalance. And this imbalance comes, well, all sorts of nuclear physics going on in the sun, but the main point is that it's there at all, and it's there because of gravity. And if it were not for the gravitational, the freedom to gain from clumping from the previously uniformly distributed material, we wouldn't be able to live off it. So the key point is that the uniformity, the low entropy in the gravitational degrees of freedom is what we live off. Okay, now this tells us, if you go right back to the Big Bang, that the Big Bang is something, you see the Weyl curvature describes the gravitational degrees of freedom, so these are more or less set to zero. So the singularity in the Big Bang is very curious. The Weyl curvature is more or less set to zero. So we have this enormous contrast between past type singularities, as far as we know, the Big Bang, and future type singularities in black holes, which are just not like each other whatsoever. And people have tried to say that they're the same part of the same story. Sure, well, why not? Quantum gravity would be the answer. Surely we're looking for a quantum gravity theory to try and explain the singularities, and you don't have singularities because maybe they are somehow tempered in some way by quantum gravity. Maybe so. But if it's quantum gravity which deals with the singularities, it's a very, very peculiar kind of quantum gravity, which is completely asymmetrical with regard to time. And this is what I believed for a long time. that we're looking at a theory, looking for a theory, which is completely asymmetrical in time. And in fact, there are reasons to believe that quantum gravity, whatever it is, or that, let's put it like this, in a different way, I'd rather do it, the combination between general relativity and quantum mechanics is a very peculiar combination. Why do I say that? Because gravity has this remarkable feature, which no other field in physics has, is a principle of equivalence. And here we have in the top picture, maybe Galileo, I don't suppose he actually did it himself, but he was considering the situation of dropping a big rock and a little rock from the leaning tower, and they fall together. So as they are falling, you cancel out gravity. It has a principle of equivalence. It's the only field in physics which has a principle of equivalence. And this is the feature which general relativity is based upon. So Einstein was able to produce a theory based on the principle of equivalence. That is to say that locally you can cancel it out by falling freely. It struck me as a huge irony in the history of science that the theory which developed science, basically, Kepler and Galileo and then Newton's Principia, and he studied all sorts of other forces, not just gravity, but and this basically, the understanding of forces generally leads to other kinds of forces, electromagnetism and particle physics and all kinds of things, all these other forces in the general framework of Hamiltonians, Lagrangians and things like that, which encompass it all. And yet general relativity is in some sense the exception to all these things. It's the curious kind of a perfect example, but nevertheless, it's also an exception. And general relativity had to be based on this exception. Here we have a futuristic space station and the astronaut floating freely because of the principle of equivalence. And without, even though the Earth is right there, the astronaut barely notices the presence of the Earth. And that is the curious feature of the general relativity. Now, here you can, as a calculation which one can do, if you're imagining an experiment on a tabletop and you want to consider the Earth's gravitational field in this calculation, there are two ways you might do it. One is using the normal way that particle physicists or quantum mechanic people would normally do, which would be to put a term in the Hamiltonian and then go calculate as normally one would do. And you do it that way. That's the Newtonian perspective. Or the Einsteinian perspective, which is saying, no, no, don't do it that way. You consider a falling frame, and in the falling frame, there is no gravitational field. So there are two ways of doing the same calculation. And what's rather remarkable is they almost come out the same. Almost, only almost. Because what you find is, and I have the purple coordinates, I think are the freely falling ones, and the green ones, I think the Newtonian perspective. The difference between them is a phase factor. So you might say, who cares? It's just a phase factor. You only could square the modulus anyway. But you look a bit more carefully, and you see it involves a term involving t cubed, an exponential of the t cube, and then involves the square of the gravitational acceleration field. And so that tells you that you have a different vacuum. So you have different vacuum for the Newtonian perspective from the Einsteinian perspective. Then again, you might say, who cares? Stick to your vacuum and you're all right. That's okay until you start to consider a superposition between two different gravitational fields, and then you do start to worry. So I imagine here you put a lump of material, it's not just the Earth field now. In your experiment, you're considering a superposition between two gravitational fields, and then you try to use the Einsteinian perspective. The Newtonian one you could do, of course, because just like any other force. The Einsteinian one would be saying, no, it's like an acceleration. You get rid of it locally, but you can't do that globally because this thing doesn't extend globally. So you're in trouble. All I do at this point is to say you try and take the measure of the error, integrate it over space, and you get an uncertainty in the energy measurement, and then you say that gives you a measure of the lifetime. I don't want to go into that, but it seems to me there are strong arguments you can make that the effect of gravity on quantum mechanics is going to be much more important than the effect of quantum mechanics on gravity. And the point I'm making here is that if you try to accommodate the principle of equivalence you are led into this picture, which, well, Diyoshi produced this collapse scheme originally, and then I picked up on it using the type of argument I just showed you, which showed that it really is intrinsic to the Einsteinian perspective for general relativity, which gives you a lifetime for a superposition. So I'm trying to say that the measurement problem is really a problem. I wouldn't call it quantum gravity because it's more like gravitizing quantum mechanics. It's the combining of gravity with quantum mechanics is not going to be a unitary theory. This relates to, I'm sure we will have see this kind of argument presented by other people later on, which people call the paradox of information, or information paradox in general relativity, of collapse to a black hole, and then the information seems to get destroyed. And how can that be if you want a unitary theory? And if you draw the conformal diagram, you can see that the singularity is space-like, and it's very hard for me to see how you could possibly get the information out, because it's just, unless you're going to violate the no cloning in quantum mechanics or something like that, you're going to get your information destroyed on the singularity. But to me, that's not a problem. It's not a problem because general relativity, I mean, quantum mechanics as used with the measurement issue, that is to say, you collapse the wave function as you see quantum mechanics applies to the world, is not unitary. And I'm trying to say that when gravity is important, you're going to see it manifestly not unitary. Now, I know this will be not the sort of view that is expressed by many people. They claim that you want a unitary theory of quantum gravity. I'm trying to argue that considerations of black holes and so on tell us that it's not unitary, and considerations more of the ones that I was just giving you, which is giving you a lifetime, which is the energy uncertainty. You take the reciprocal of that. It's like the time energy uncertainty, Heisenberg. If you've got an energy uncertainty, this gives you a lifetime. Or you usually argue the other way around. If you have an unstable nucleus, then you have a lifetime, and that lifetime is reciprocally related to an energy uncertainty. And I'm saying if you have an energy uncertainty, which you do seem to have if you take the Einsteinian perspective, that gives you a lifetime. And so you do not have unitarity. So although I know this is sacrilege to many people, I try to say that when you have black holes, it's very much a gravitational situation. So it's not at all surprising that you get a violation of unitarity. And I don't believe that the information somehow comes back out again. So that's my view. It's not the main point of my talk, but I thought I would mention that because it is presumably going to be relevant to other people's talks later on. Okay, let me move on. Now I want to argue about the question of the singularity and how we look at it in a different way. You see, here we have the remote future. This is the cartoon of the universe expanding as I had before. And now I want to take the remote future and squash it down with a conformal map. This is a very useful trick to use when you want to talk about gravitational radiation. I'd used that for a long time to talk about the energy and gravitational radiation and things like that, which is it's very useful to squash infinity down. Those arguments in the old days considered asymptotically flat situations, but now we know there is something like a cosmological constant, and that means a positive one, and that means that the future infinity is really space-like, rather than being null as it was in the early considerations. So you have a space-like infinity, squash it down, and you can talk about the remote future, the radiation, and if it's mostly photons, if it were entirely photons, then you would say that there would be no way of scaling. I'll come to that point a bit later on, but you can squash down infinity, and in squashing down infinity, you also, the very dense and hot universe, the very rarefied and cold remote future becomes squashed down to be something which would be not so cold, not so rarefied. What about the Big Bang? Now, this was a way of looking at the early universe, rather than saying the Weyl curvature goes to zero, which was just the postulate, which I was mentioning earlier. My former student, Paul Todd, who became a professor, now he's retired, like, I guess that tells me I've reached an ancient age when all my graduate students have retired from being university professors and things like that, or whatever they became. And that was the case. Paul Todd is retired, but nevertheless, he introduced this idea and calculated with it very important work by saying, you don't just say the Weyl curvature is 0, you say that the Big Bang, when you stretch it out conformally, it becomes smooth. So that was the idea, that you can apply these two tricks. You can squash down infinity, you can stretch out the Big Bang and make them both smooth boundaries. And that is a much better way of talking about the specific condition on the Big Bang. There has to be some enormous constraint on the Big Bang, which gets rid of all these complicated, horrible possibilities that don't occur, somehow which kills off the degrees of freedom in the early universe. It's purely a hypothesis again, but nevertheless, when I began to think about this, it seemed to me that these things look awfully similar, because the Big Bang is very hot and dense, but when you stretch it out, you get something which could be compared with the very remote future. So although this is quite a nice picture like here, it's a nice picture, and it could be a good way of describing the universe. But here I want to say something which is more of an outrageous thing. Well, first of all, before I talk about that, I'll talk about the squashing down of infinity, which is nicely illustrated in this Escher picture, where you see that the boundary, it's a bit, well, you can see how the angels and devils, this is actually a hyperbolic geometry, but in hyperbolic geometry, it's very nice. You can represent it within the, it's what's called the Beltrami, well, people call it the Poincaré disk, but actually Beltrami had it first. I think even Riemann had almost this picture, but you can see that it's a conformal picture. You see the eyes of the fish are circles, and they remain circles right out to close to the boundary. And that's a nice illustration of the conformal nature of the picture. And you do something similar to the Big Bang. Now, there's a feature here which is important also. Here we have the two most famous formulae of 20th century physics, Einstein's E = mc squared and Max Planck's E = h nu or hf. And the combination of these two equations tell you that not only is energy equal to energy and mass are equivalent, energy and frequency are equivalent, but that tells you together that mass and frequency are equivalent. So if you have mass, then you have a frequency. Any massive particle is a clock, basically. The frequency is very much too high to use directly, so you have to scale it down for your atomic or nuclear clocks, but still they're so perfect for that sort of reason. So that the feature is that mass gives you time. If you just have massless, that is the photons, then you don't see these surfaces which tell you what the first tick and the second tick and the third tick and so on. Clock, which is given by mass. The converse to this is really when you don't have mass, you don't have clocks, and therefore you have conformal geometry. So the idea of conformal geometry is the geometry when you have no mass. Now, this is the picture here, which I was saying before. When you have no mass, well, what about the remote future? Well, it's pretty well dominated by photons. You will have, as far as we know, particles running around with mass, hydrogen, even a lot of hydrogen running around for a long time. I want to postulate that there is in the very, very remote future, a feature which kills off mass. This is unconventional, perhaps not so stupid, because one of the ways one classifies particles, and the first thing you do in particle physics is to write down the Casimir operators for the Poincaré group. The Poincaré group is basically supposed to be very fundamental to particle physics, but if you have a cosmological constant, you can certainly argue that perhaps the right group is the de Sitter group. And the de Sitter group, when you look at the Casimir operators, you find that mass is not a Casimir. So that if you're looking at time scales of the order of the age of the universe sort of thing, then you might expect that maybe mass is not such a good parameter. This is a speculation, which I don't have any theoretical justification for, except that it lies open, the possibility that you might have a mass fade out in the very remote future, and which is the postulate which I'm saying, that the physics in the remote future, so it's not just photons, but that all the mass will become zero mass initially. The Big Bang, what about the situation there? Well, it's more or less the opposite, but with the same conclusion. That is to say that the energies of particles get so high that they're moving around so fast that the mass becomes irrelevant. Of course, that does depend on the particle physics to a certain degree, but nevertheless, the general argument is that mass becomes irrelevant at the Big Bang, and as you approach it, it's big massless physics again. So the postulate here is that you have massless physics at both ends, and that the Big Bang very much resembles the remote future, and that is the picture which I'm postulating here. This is outrageous. I'm saying that our Big Bang is the continuation of the remote future of a previous eon. And this automatically will kill off the Weyl curvature, because in fact, if you look at the remote future, you find that the equations, some work due to Helmut Friedrich, most particularly, shows you that you do expect to have the Weyl curvature going to 0 in the remote future. And it's quite easy to see that that is a generic sort of situation, that the Weyl curvature becomes actually 0. It's not that it becomes finite, it becomes 0. And so that you have a stronger condition on the Big Bang. That the Big Bang, the Weyl curvature is not just finite, but it's 0. And that is a condition for this model, that our remote future becomes somebody else's Big Bang. Our Big Bang was the continuation of somebody's remote future, going through a phase where the mass was effectively 0. Of course, you need equations for that, and one can write down equations, and various people have slightly different equations. I don't want to go into that in detail. The main thing I do want to say is that you can consider this situation. And I remember for a long time, I had this view, I can't remember how many years ago it was, over 15 years ago. And I remember thinking that I go on talking about this forever and nobody would ever be able to prove me wrong. But then I began to think, well, maybe there are observations who could test this theory. And the first idea that I had about this was the idea, well, you could imagine signals coming across. If you have massless signals coming across, maybe very, very low frequency photons, sort of magnetic fields or something could get across. But what about gravitational wave signals? Yes, indeed, they ought to be able to get across. So you could imagine that a strong enough gravitational wave signal could get across this. I should say the line in the middle is meant to be the crossover between the previous eon down here and the future, our eon at the top here, and signals could get across. So if you had a powerful enough gravitational signal, maybe that would get across. And then I began to think of what could they be? Well, you see here I have in the middle, we have the crossover between the previous eon and the future eon. That's us right at the top looking back. And in the previous eon, I'm calling these different eons, if you like, we have two supermassive black holes colliding in a galactic cluster. You might expect that this happens many times. So they would collide again and again and again. Each time this happens, you find a ring. You have to add another dimension, of course, so that the intersection of these, this would be a sphere. Our past light cone would intersect the surface of a sphere. The stretched out Big Bang would also be a squashed down remote future of the previous eon. And these signals coming out from the collapse would look like other spheres. The intersections of them would be circles. And so you would have intersections of circles. If this happens in the same galactic cluster many times, you will have concentric rings. And this was a signal that my colleague Vahe Gursajan looked for. I may say there's a lot of argument about these things, but let me show you this picture, which is hard to argue against. This picture shows you in the Planck data, the centers of, you see, he looked for rings of low variance. So he didn't look for the rings being warmer or cooler than the rest, but the variance of the temperature around the ring should be a little smaller than normal. And the signal is not strong enough for a single ring, so you look for triples of concentric rings of low variance, and that's what he looked for. And I'm just plotting, I'm not worrying about the significance or anything, I'm just plotting the picture here. Now the picture shows you in the Planck data where the centers of triples of low variance rings are. And it's extraordinarily clumped. It's not uniform at all. So whatever the source of these signals is, it's got to be something very non-uniform. Now you can understand the non-uniformity if it's a very large-scale non-uniformity in the universe. This, of course, goes against the cosmological principle. People who don't like not to believe this, but how do you explain this picture? Now, you see, I want to point out that the color also is different. And I point out that he was looking for low variance. He wasn't looking for the temperature. The color is the temperature. Now, red is awfully complicated because there are two reversals of the red actually means distant here. These are the cooler ones. That's right. The red ones are the cooler ones and the blue ones are the warm ones. The main point is that the red ones, according to the theory, were very distant. Now, you see, the clumping is not just in where they are in the sky, but in their color. Now, why is that? Now, in the theory, it makes sense because you have a huge distribution of very, very distant galactic clusters here. Here we have a much newer, closer one within our own past particle horizon. This would be outside our particle horizon. Signals can come from outside the particle horizon in the scheme. As you can see, the geometry still works because you can get through from one eon from the other, and it can be outside, which is normally considered to be our particle horizon. But the red ones would be clumped together, very, very distant, and the blue ones within our particle horizon. You might see effects perhaps in quasar distributions. In fact, there does seem to be some effect there. I won't stress that because I think the information is evidence is quite weak. But I just say that this is hard to explain this picture. Whatever you regard as the explanation for the signals, you see this picture, and it seems to be there. I haven't seen anybody contradict this picture. The other argument I want to make is to do with the black hole evaporation. I had a picture of this before, but let me consider this again. You have to wait an awful long time because before black holes start to evaporate away, for the really big ones, something like Google years, 10 to the 100 years, maybe 10 to the 109 years, I think was John Page's claim, something like this, I forget exactly. But you have to wait an awful long time before they evaporate away. But nevertheless, it's still there in the, sorry, I'm going the wrong way, picture. This is a picture from a paper by myself, Christoph Meisner, and Pavel Nurovsky and Daniel Ann in the monthly notices of the Royal Astronomical Society, getting on for 2 years ago. I haven't seen a single comment on that paper. I've seen comments on the paper which was on the archive, which is somewhat different from the actual paper. Maybe there are comments on this paper. I've seen several in the archive, but nothing that contradicts the data we see. Maybe the way that the analysis is done, which one could go into later. Here I see, this is meant to be, this is the picture that we have from it. The horizontal line at the bottom, time is going up the picture, at least for the bottom part of the picture. Here we have the crossover from the previous eon. Here we have the world line of a supermassive black hole. Its evaporation does not even start until almost infinitesimally below the crossover surface. And so it comes through at one point, spreads out through 380,000 years before it becomes part of the microwave background. And then you will see a spot in the sky. And the size of this spot is a bit interesting because what we tend to see is about 4 degrees across in the sky, which is 8 times the diameter of the moon, something like that, of the full moon. From standard calculators, it's pointed out by Alan Guth, which we claim that we see these things at a size of 8 times the diameter of the moon. And according to particle physics calculations, it should be about 5 times the diameter of the moon. Well, that's a little bit curious, but Christoph, who knows a lot more about particle physics than I do, says there are a lot of assumptions which go into this, and it's a bit hard to estimate and exactly what that estimate is. Depends on renormalizations at various points, and you have to, well, I just may say. But anyway, what we do see is spots which are about 8 times the diameter of the moon. And these spots are seen with a confidence level of something like 99.98%. Now, there is a slight point about this, is because that's what we see for these spots being 8 times the 4 degrees across, about 8 times the diameter of the full moon. And it's a very clear signal of that size. If you consider that they could be of other size, then maybe you should reduce that to something a bit less, but it's certainly not less than 99% confidence level. So it seems to me that the signals are there. We have to explain why they're there. I should explain also that not only are they seen in the Planck data, if you look at this 5 strongest spots, I'm not sure I would trust all of the locations, but if you look at the locations of the 5 strongest spots in the Planck data, now we look also in the WMAP data, and we see those 5 spots are in exactly the same places in the WMAP data. There's also a 6th spot, which is just about as strong in the WMAP data. We look back in the Planck data, and it's there too. So I would say those 5 strongest spots are definitely what I'm calling Hawking points. They're whatever the explanation for them is, they do seem to be there with a good, strong confidence level. And whatever the explanation for them is, it's hard to explain on the conventional theory. So I would like to hear people's comments on this. And this is all I have to say for the moment. Thank you very much.
Thank you very much, sir. It's a very interesting talk. And there are many questions. The first one, it is from Hammam. He said, thank you for this wonderful lecture.
Professor Sandouk, I think Professor Hooft want to speak.
Pardon? Okay.
Yeah. Professor Hooft, please welcome.
Yes, may I ask the following question? Can you hear me?
Yeah, I can, yes.
Okay. Well, at the black hole horizon, did you look at all how ingoing particles interact gravitationally with outgoing Hawking particles? My claim is that that can restore unitarity for the entire system of black holes. And then
do you say the Hawking evaporation, I mean, do you agree it occurs?
Hawking evaporation can be reconciled with unitarity if you take into account interactions between the ingoing particles and the outgoing particles. That's my claim. And I can add to that the other question to you, which is, don't you need unitarity to ensure that probabilities add up to 1? I think in most physical theories, they do.
I don't think you see, I don't know how you continue with unitarity and maintain measurement. You see, measurement takes place. For some reason, people insist on unitarity when we observe things in quantum mechanics, unitarity is violated. It's almost always violated in the measurement. So
not the kind of unitarity that you need to understand that probabilities add up to 1. Is that violated, even if you measure things?
But you have amplitudes. How do you get probabilities out of amplitudes without having a measurement? You get amplitudes. In unitarity, you talk about amplitudes. You don't.
Quantum mechanics is a set of rules, and there are rules that tell you how to compute probabilities of anything. You can then measure and see whether that's true, but in practice, that's obviously true.
I know this is dogma, and I understand the dogma, but I don't believe the dogma. The dogma somehow is that you insist on unitarity because somehow you don't believe that measurements take place. I'm not quite sure how that works.
Well, measurements are part of this universe as well. So we do experiments,
unitarity.
But don't you believe that probabilities add up to 1? If you make a good theory, you compute the probability for this, for that, for that. But that's what unitarity is.
No. Unitarity, you see, how real do you regard the state? I guess it's a question of whether you regard the state as something real physically or not.
Yes, I do. I'm going to
explain
that.
If the state is real, then you don't ever have measurements. Well, I mean, except occasionally when you're actually measuring an eigenstate directly.
We saw in previous talks people measure a lot of things, so why not?
No, I'm saying something completely obvious about quantum mechanics. which seems to be ignored, and I don't understand why. Either you're going to in many worlds view or something about quantum mechanics, in which case you've got to.
No, I'll explain in my talk how I view quantum
Yes,
mechanics.
all right, I have to wait for your talk. But in my view, is you're taking quantum mechanics as we see it. And quantum mechanics says that you evolve the state according to the Schrodinger equation, which, yes, unitary, yeah, you avoid it at that.
Yes.
And then at a certain point, you say measurement takes place. And when you say a measurement takes place, you violate unitarity, because you say that you have a probability mixture of a number of different states. You don't say you have an amplitude mixture of a certain number of states. The state is an amplitude mixture.
It's somehow identical to add up to 1. You can square the amplitudes and then say that's the probability, and they add up to 1. So what else do you want?
I want them to be, the state is not, well, what do you say reality is? Do you say that reality follows the Schrodinger equation?
No, I'm going to explain that in my talk.
Yes, that's your talk.
It's difficult to say in a few words like this.
Yes, but I can't understand this point of view. I know it's held by many people, very, very distinguished people such as yourself. I certainly agree with that is a view held by people, but I can't make sense of it. As Einstein couldn't make sense of it, Schrodinger couldn't make sense of it, Dirac couldn't make sense of it, because they all claimed that you did need to have some extension of quantum mechanics.
That's a mistake.
Well, you say that's a mistake, and maybe, okay, you've got other distinguished people on your side too. I agree with the fact that there are many people who take that view. It's not my view. My view is that the state is described by the wave function for a while, and then it jumps. As the measurement takes place, involves a jump.
I'll explain in my talk that you don't need that jump. That jump always, nature takes care of those such jumps as soon as you measure something.
Yes, but I'm talking about my talk at the moment.
Yes, I understand.
Your talk later. My talk claims that measurement is a process which violates unitarity. And I also claim, by the little argument that I'd give, that if you want to preserve the principle of equivalence in general relativity, you're in trouble if you want to preserve unitarity. And I think that argument needs to be looked at carefully.
Don't you agree that quantum mechanics is a model to compute the probability that this happens, or that happens? And don't you agree
it does
that
not,
those outcomes, whatever they are, they should add up to 1?
It does not, the model does not have a consistent ontology. The model changes its mind about what the real world is doing.
Yeah, I agree with you.
After the measurement, the real world is the result of the measurement. Before the measurement, the real world involves an amplitude superposition of the different alternatives. That is an ontology shift. Now, okay, you can take that view. It works very well, and I certainly agree it works very well. But it's not a consistent ontology for the universe. A consistent ontology would require that the state jumps according to the measurement process.
Well, these are long stories and not easy to explain in a few words, but I can explain how the wave function actually collapse actually takes place or not. And you find that this is just very simple, straightforward mathematics that
completely
the equations are rather simple. So we cannot disagree about the equations.
It's the question of the ontology. How does the mathematics relate to the world? It's not a question of the mathematics by itself. It's how does the description of the world, according to the mathematics, how does it remain a good description of the world? And you jump when you use your action.
Even in a classical theory, but maybe other people want to ask questions as well. I don't want to continue much, but even in a classical theory, you can throw dice and you can ask what happens to the dice before you throw them and after you throw them. Did the probabilities change? And the answer is obvious. Well, take your dice, throw them, and you see what happens. It's very easy. You could do that in the Stone Age and have no problems with understanding that the probabilities make a delta jump whenever the dice come in a certain position.
It's when you make a measurement. What do the dice come?
Yes.
You look at them.
And then you look at them. So we all agree about what we do physically.
I'd rather we move to another question because I think we're not going to get anywhere with this one.
Okay, I agree.
Sorry about that. Do we have any other questions?
Sandouk, unmute your mic, please.
There is a question from Hammam. He said, thank you for this wonderful lecture, Professor, and I am big fan of you. My question is, do you think that we can have an absolute concept of black holes in the future? And what is the most thing that makes a black hole lose the largest amount of energy?
Well, the argument is the Hawking process. Okay. You see, I mean, in fact, the picture that I presented in my talk does not, strictly speaking, depend on the Hawking process. You see, the Hawking process tells you that when the temperature, first of all, it tells you that the black hole has a temperature. So Stephen Hawking was able to show that black hole ought to have a very, very low temperature. Now, it's so low that you don't normally worry about it at all. But when the universe expands and expands and expands and it gets colder and colder and colder, it comes to a point where the ambient temperature of the universe is lower than that of a black hole. The smaller ones are the hottest ones, the biggest ones are the coldest ones. So you have to wait a very, very long time before the ambient temperature of the universe gets lower than that of the black hole. Then, according to Hawking, and I think the argument is very sound, the black hole will lose energy in radiation. This energy will then reduce the mass of the black hole. It gets smaller and smaller and smaller, and eventually it disappears. Now, it will disappear. Some of the information or energy or whatever it is, the information in the black hole will go in the radiation. Some of it will get destroyed in the singularity. How much is which doesn't make much difference to my picture. But the black hole will eventually disappear. And I am perfectly in agreement with that. It does not really matter too much for the argument that I gave. They could even be, the black holes could last forever. They would simply come through into the next eon. And as far as observations are concerned, I can't see any distinction between the nature of the Hawking spots, as I'm calling them, if the black holes evaporate away or not. But I'm quite happy with them evaporating away completely. Right at the very last point, when they disappear, they become Planck scale object or something. You have to violate ordinary, well, you probably have to bring in quantum gravity at that stage, which is fine. But they eventually disappear. I don't know if that's the answer to your question.
Okay. There's a question from Muhammad Ismail. Thank you. Between mathematics and physics, can we say that the center of whole singularity have a percentage diameter of a Planck length?
I don't think we can say anything about it at all. Mm-hmm. You see, we don't really know anything about the nature of the singularities in general. They're probably extremely complicated. Okay. If you follow up the work, the Lifshitz and Kalatnikov and Belinsky, and also Misner, the works that they discussed in complicated singularities, they are very, very complicated. And what you can say about the size of the singularities hardly makes any sense. I think a Planck scale would be a reasonable thing to say, but the physics of that scale is completely unknown. Of course, maybe some people think they know the answer to the Planck scale physics. In my view, we don't know, but it doesn't really affect anything. You see, the picture I'm presenting is that the singularities, roughly speaking, come through as the Hawking points. You see the spots on our side, the galactic cluster basically ultimately almost gets swallowed completely by a black hole. This black hole eventually evaporates away, maybe, or maybe it sits there forever. I think it evaporates away. I think Hawking was right. It evaporates away. all that radiation that's evaporated away comes through as to a single point in the next eon. That single point is much, much smaller than a Planck scale. So in the initial Big Bang, those little points, who knows what goes on there? I would say that you have to lose information. In fact, that's how you have a second law of thermodynamics, which makes sense, because you have to destroy the information that was sitting inside the black hole, if you like, or was either sitting in it or in the Hawking evaporation. It makes very little difference in the picture because the Hawking evaporation and the black hole itself is simply concentrated in a Planck scale, low, much smaller than Planck scale. And therefore, who knows what the physics is on the other side. It's basically an injection of enormous amount of energy at that point, which spreads out to something like 8 times the diameter of the moon. There's a little bit of argument about how big it should be, as Alan Guth had certainly pointed out at this point, somewhere between 5 or 8 times the size of the moon. What we seem to see is 8 times. And that's where the energy goes. And we see it. We see it in these spots.
Okay, we don't have enough time. Just there's this is the last question.
Okay.
What is the rule of the singularity in a black hole merging?
Well, they would tend to congeal, I expect. Well, you see, it's very hard to know because the singularities, each one would be space-like, and they would probably form a big space-like region. Now, you see, the trouble is the size of that is less than the Planck scale when you come through. We can't really talk about it because the physics is completely unknown. You have very high curvatures, and in some sense they congeal, but they don't congeal in any sense which allows them to influence each other, because I think they're space-like separated. In the pictures that one tends to draw for a single black hole, the singularity is space-like, so that the different parts of the singularity are separated. They're not even causally connected with each other. So that when you have 2 black holes congealing, they're more space-like, if you like. They have nothing to do with each other. And they destroy, the space-time gets destroyed before there is time for them to communicate with each other, if you like. I mean, that picture may be wrong because quantum gravity of some sort, whatever quantum gravity is, could come in and change the picture at that point. But it's not much use to us because it's not observable. It's all inside the black hole. So the trouble with talking about the physics there is it doesn't have any observational implications as far as I can make out. I mean, maybe ultimately there would be in the Hawking points, maybe we can examine these spots carefully enough to know something about the nature of the singularity. But I don't see anything close to that at the moment.
Thank you very much, sir. And I am sorry for the others because we don't have enough time to answer. There are a lot of questions, but I am sorry for we have not enough time. Now we have to go to the second session, and I am going to leave you with my colleagues, Professor Alfasi. She will introduce the second session. Thank you very much.
Good morning. Can you hear me well and see me?
Yes.
Yes. Good morning, everybody. So we are honors and pleased to receive Professor Gerard Hooft, who is theoretical physicist and professor at Utrecht University. Professor Gerard was awarded the 1999 Nobel Prize in Physics, along with Professor Witten, for elucidating the quantum structure of electroweak interaction in physics. So today we are really delighted that Professor Gerard had accepted our invitation, and he will talk us about the foundation of quantum physics and the standard model of the elementary particle. So Professor, the floor is yours.
Thank you. I wonder whether my slides go through. I hope, well, let me see. This share. Yes,
Yes,
my slides
yes,
now?
yeah, I confirm. We
Okay,
can
very
see
good.
your slides. Please go ahead.
Very good. So it's my great pleasure to join previous speakers in congratulating the APS for with its establishment. I hope it will have a very marked effect of Arab physics in the Arab countries, which of course has flourished long ago. I'll mention that briefly, but we hope it will again flourish as well as in past times. So I just looked at the website of the organization, and some statements that were made was it is there to promote excellence and creativity in the field of physics. And later it says, spread physics education and knowledge through conferences, seminars, workshops, summer and winter schools in the field of physics. And you can go on with this. So I think that's exactly what we are trying to do also today. However, scientists are almost like ordinary people. Over the centuries, their attitudes towards their mission changes. And I want to emphasize on these changes that take place. They take place very slowly. Our task is to detect systematics in how the world is structured, to use our findings for the better of mankind, but also to design new tools for making our next steps. And making our next steps is one of the most exciting things you can try to do as a scientist. We have many success stories, but progress is slow. Apparently, centuries are needed to generate new insights that not only enable us to get a better view of reality, but also to formulate our next questions and to judge our answers. On this slide, I start with thousands of years back when science was sort of mixed and spread out and was very slowly proceeding. As I said, the Arabs played an important role in that process. I won't go too much into those details, but except for mentioning how that period, the first period from my perspective, ended with Newton, Huygens, and then later the mathematical physicists like Lagrange, Hamilton, and Laplace. They set up important schemes for how you have to do how do you have to understand the dynamics of forces, of particles, of objects, of planets and stars, and so on. But so they discovered, particularly for instance, Maxwell and Faraday, that you can also unify other forces of nature, in particular electrodynamics, to put it at the same status as gravity theory as Newton had established it in his time. So that was a climax in scientific developments. But then a new golden age was beginning more or less exactly around the year 1900, when the first signs of quantum mechanics became evident. And then shortly after that, Albert Einstein made his discoveries of new theories. These initiated big changes in the way people thought about how to do science, that there are theories which are counterintuitive, which you have to dig up from the deep, so to speak, which will change your view of reality drastically, as discussions in this meeting also have shown. So there was a big shift in attitudes among scientists about how to do science. You do science because you have theories about reality. You do experiments to see to what extent these theories make sense and agree with what you think they do. And then you make tremendous new kinds of progress. So we discovered general and special relativity, the atom, discoveries of new materials, particularly things like superconductivity, and at the same time, parallel astrophysics took enormously big steps in understanding our universe. And another marked period was reached around the 1960s, I believe, when people said, yes, it all works, but we have a problem that somehow we cannot address properly. And that is the problem of reconciling the physics of elementary particles, reconciling that with two fundamental theories. One is special relativity, and the other is quantum mechanics. So both special relativity and quantum mechanics were understood, but it was not understood well how to combine these two into one. And people thought there were paradoxes, there were mistakes, something was very wrong in the way we were thinking, until, that's very important, until people understood how to apply the knowledge of quantum mechanics and the knowledge of special relativity to formulate quantized field theories. So yes, the elementary particles didn't seem to obey all these principles, but when you regarded those particles as the energy quanta of quantized fields, then everything fell in place again, and you could make your progress. At that time, around the 1960s, there was also big opposition against quantum field theories. Something was wrong about them. But then, after that, we discovered how to cure these diseases, and that was where I received the Nobel Prize in the investigations of how to do this, for instance, for the weak force. But the weak force is just an example of interactions. But there we found that the gauge theories were the way to go. And from then on, the scene opened for new possible ways to proceed. And then we entered the modern ages until right now, where again we use different principles than before to make progress. And what was learned in those days was how to use symmetries, how to apply Lie group theory, advanced versions of mathematics, like the Virasoro algebra, the Kac-Moody equations, and all that. And all this led again to marvelous progress. There was string theory, superstring theory, new theories for quantizing gravity or attempts to quantize gravity, such as supergravity. And all these new, quite abstract principles seem to be extremely promising. But right now, to me, it seems to be again approaching a stage of a stationary understanding. We are proceeding slower and slower to do our next step, because now our problem is not to reconcile quantum mechanics with special relativity. Now our problem is, as previous speaker has talked about, how to reconcile quantum mechanics with general relativity. We have reached that point now, and we do not know how to do it. And I think, again, new fundamental steps will have to be made in order to do that. And I think we have to drop some of our admiration for symmetries, the symmetry principles. They are not the whole story. And I think the whole story is this, that in today's physics, people still seem to believe in miracles. They don't quite understand what they're doing. In string theory, I've seen it several times, that people say, we don't actually understand what we are doing, but we believe the equations of the theory. And then we believe that miracles will happen, everything will fall into place. And as these colleagues are arguing, yes, but we are not quite happy with those miracles. Well, I am not happy when people talk about miracles. I think there are no miracles in a truly scientific description of nature. There are only equations and logical arguments and derivations. No miracles. So we should now abandon the miracles. And that is what I claim will prepare the way for the future. Quantum mechanics is often addressed in a sort of mystifying way. People don't like the idea that quantum mechanics can simply be understood as a feature of nature without any fundamental difficulties. So and now I'm going to approach where the weaknesses are in still today's general approaches to understanding particles. This is that the same quantized field theories I just talked about are often shown to have difficulties, and which people admit, but then they systematically ignore the difficulties that the theories have. Not everybody, many people complain quantum field theories are less than perfect. Mathematicians don't like to do quantum field theory because they say, well, we don't quite understand, you're making things too complicated now for us. And we don't even understand the definition of a quantum field theory. Because what people often do is they say in a quantum field theory, we have the so-called Feynman rules, and the Feynman rules tell you how to compute something. But the computation is an infinite sequence of computations, and the sequence doesn't stop, and we don't know whether the sequence converges. Actually, very likely the sequence of calculations doesn't converge at all. So quantum field theories are not really perfect. And not only that, so the perturbation theory is fundamentally divergent. On top of that is the fact that even if you go to any given order of perturbation theory, you encounter Feynman diagrams, and when you do the appropriate calculations for that, you find those diagrams to be divergent again to generate infinities. And we should be content with the situation. We should do something about these infinities. And what Veldman and I at the time did was very carefully study those infinities and see how they can be renormalized away. That was a successful program, but it didn't mean that all the other difficulties of quantum field theories were completely solved. In fact, we just said they are now good enough to use in practice. Now, in practice, we don't do infinitely calculated measurements, infinitely accurate measurements. Our measurements are only approximate, and for that, the quantum field theories are good enough. But they're not good enough if you want to really understand how they are defined physically. And to come to that, I think the only way to do that is to ask new questions, but we have to ask new questions from the very beginning of where we have the foundations of our modern science. Much of what we think today is founded around at the beginning of the 20th century. In around the 1920s, a group of very smart physicists came together in the discussions, often in Copenhagen, and they reached agreements on lots of things. They basically discussed quantum mechanics, and they agreed about what quantum mechanics says and how to work with it. Now, equations, you can get those equations by studying the corresponding classical theory. You make a few substitutions there, then you get the quantum theory, and you don't have many options there, so you get a simple looking set of equations. You can now solve those equations, and lo and behold, if you follow the rules, you get very precise predictions of what is going to happen, and the predictions agree with the experiments. However, there was one point where further discussions continued, and the continuation was, the discussion was, what is it that you are describing? What are these equations really saying? They tell you how to compute something, but in terms of what? What is the reality that's going on? The ontological reality. We just had a brief discussion, Penrose and myself, about ontology in quantum mechanics. And the problem was, what's happening if you do quantum mechanical calculation? But then the Copenhagen group did something very clever. They said, we can reach agreement here. We just agree to disagree. We agree that there may be different ways to interpret quantum mechanics, but we don't care about that. We just ignore it. So don't ask that. Just ask, what will the experiment say? What will be the outcome of this experiment? And the outcome of the experiment will be that particles fly all over the place with certain statistical probabilities in this direction, with other statistical probability in that direction. And the theory is very good in giving these probabilities. And in fact, it's the best answer that you can get out of the theory. So this was a big success. The rule was shut up and calculate. And this entire package, including shut up and calculate, is now the Copenhagen interpretation, at least the way I see it. It is entirely correct. It works perfectly. There's nothing to complain about. And it's survived for almost a full century now. But I don't agree with it. I don't agree with that last verdict that you shouldn't ask what's really happening when you do a quantum experiment. Just ignore that and go on with your calculations. That would have been fine if everything were perfect. But by asking what is truly happening, yes, you will learn a lot about the physical world, my claim, than that you did not yet know before you really asked the right questions. So again, you have reached a period that question asking is very important, and it's very important to change how you formulate something, how you formulate your question, and how to address the question, how to answer it. So a typical example is now the standard model of the subatomic particles. Because this standard model contains quantum field theories, and there we can use very well to compute probabilities, if not perfect. Well, they work to enough decimal places so that you don't have to worry. That is the standard statement. And but there are some things that the theories do not tell us. And what they do not tell us is the strength of the coupling constants between the particles. So we have a gauge theory, it works perfectly, it tells you all these things about neutrino oscillations, the first speaker, and it tells us how the universe evolves, second speaker. But there are interaction strengths, and the theory does not tell you what these strengths are. We have to measure them, and these measurements can be done. That's what science is about. So we get certain values, and that we have to play with. And then finally, I should add, there's one very mysterious constant, the cosmological parameter, cosmological coupling constant. The most mysterious thing about it is, well, there are two mysteries about it. The two mysteries are, why is it so small? It should be much bigger if there would be any constant like that. And then the next question is, why is it so small, and yet why is it not zero? Those are two very important questions, and the answers are not coming from quantum mechanics. So quantum mechanics as a theory is not complete from my point of view. So the motivation of investigating these things is that these difficulties culminate when we try to reconcile gravitation with quantum mechanics. And you've heard from the previous talk that there are many wild ideas about this. Some ideas are wilder than other ideas. We all have ideas about this, but none of us has come with the right answers, because we cannot make a single prediction what general relativity does with quantum mechanics, or the other way around. My claim is that today's obstacle is our lack of understanding of what quantum mechanics really is. We should ask that question again, but now ask it in a much sharper way. And the aim of my talk is to do away with a popular view of quantum mechanics that you hear very often. Quantum mechanics is something so complicated that nobody can understand it. Feynman, of all people, made remarks of this sort, that don't ask what quantum mechanics is, you won't get an answer. It's too mysterious, it's mystery. And miracles happen somehow. The miracle is that quantum mechanics works. As I said, I don't want the miracles, I just want to understand exactly what the mathematical structure of the theory is and what that structure tells you about reality. What is it that's really going on? Of course, this question has been asked many times, but the answers were less than desirable. They only added to the mystery of what quantum mechanics really is. So the misunderstanding, what I see as a misunderstanding, is the Einstein-Podolsky-Rosen paper, and then its continuation when John Bell rephrased the problems that Einstein and Podolsky and Rosen had run into in a more elegant way, so that you can test these things experimentally. And these four people actually wrote down the equation that you can test quite well experimentally now. The experiments have also been done and proved indeed these strange equations that seem to be denying the existence of a reality. Those equations are obeyed by nature, so quantum mechanics is there, and there's a total mystery. To summarize a little bit very briefly what they found is that you can do a measurement on an object emitting 2 photons. Typically, well, as a particle physicist, I know the example. The pi0 is a particle that decays into 2 photons, and those 2 photons are completely entangled. That is to say, if you know the polarization of one photon, you know the polarization of the other photon. Exactly the situation that Bell then took as an example in his Gedanken experiment, although the experiment could really be done later. And you can compute the probabilities of finding a particle going through a filter that you put in your experiment. The filter has an angle A for Ellis and B for Bob. Ellis and Bob are two experimenters. And they try to mimic what the outcome of the experiment is by writing a theory with hidden variables. And they find it doesn't work. So the only assumption was that A, B, and C should obey local laws at the same time be statistically independent of one another. And it seems inevitable then to conclude that therefore quantum mechanics is incompatible with any theory that tells you that there are just some hidden particles running around and they make everything okay. I always found that very mysterious and indirect, so I don't really believe it. And the reason why I don't believe it is that actually, if you do quantum mechanics and you compute the correlation between A, B, and C, they are very highly correlated. But it is a three-body correlation. So if you fix A, then the relation between B and C is completely erratic. But only if you look at all three of them, if you fix A, then the relation between B and C is completely random. If you fix B, the same thing. But if you look at A and B and C all together, they show very strong three-body correlation. That three-body correlation is completely in contradiction with the assumption that Bell made that A, B, and C should be statistically independent. But as Bell argued very eloquently, it's a very natural thing to assume. These photons were produced before the observers, Ellis and Bob, made their experiments. So how could these photons know that Bob was having a setting B and Ellis was having a setting A? How could the photon C have known that? So how could the photon ever be correlated with that? Well, you have to understand that if you make a deterministic theory of quantum mechanics, the answer to that question, by the way, which I'm going to give, is that you have to believe in determinism all the way. So not just make a little hidden variable which is deterministic. No, the whole world should be deterministic. And then you can say that A and B and C are all deterministic. But then you can also say that if you fix C, you can't have Bob and Ellis change their settings anymore without having some other changes in the past. So you can't change the present without changing the past. That's what the deterministic theory tells you. And that's what Bell totally ignored. And that is, to my mind, the reason why he ran into these iter-out contradictions. So, for instance, you can remove the paradox to a large extent by saying, well, let's run this whole process back in time by taking into account that the Schrödinger equation is time reversal symmetric. So if the Schrödinger equation tells you what the probabilities are in the future, it also tells you what the probabilities are in the past. But that depends on the presence, of course. So C, when A and B are the presence, C is in the past. But if you change A and B, then you will change C. And this is very difficult for people to understand. I also found it very difficult to understand myself until I realized that if you do the calculations, this is just what you get out of it. So you have to accept the equations and don't worry about them looking rather strange. So you have to solve the Schrödinger equation backwards in time to see how this works. And the best way to see how a deterministic theory of quantum mechanics works is to make the model. You write down a model and you say, this is what the model says. Do you like it or do you not like it? Do you think this is quantum mechanics? Do you not think it's quantum mechanics? I don't care what you think. I just care about the model. Suppose the whole world was completely deterministic. And that's essential for what I'm going to say next. That would mean that if you take a finite region of the universe and momentarily think of a box surrounding it, then you have a state of the universe which only contains a finite number of possible situations inside the box. And if you have a system with only a finite number of possible configurations, then the evolution law will necessarily say that it will be periodic. So if I'm in one state of the universe, which are these yellow blobs are representing a state of the universe, then the evolution will tell you the state will go into the next state until eventually it will bite itself in its tail and you'll reach the original state again. Then this is a periodic part of the universe. Now, you can build the entire universe by taking little periodic bits of universe together to get the equations, the complete set of equations for the entire universe in or for a moment constrained to a certain box. You can then later take the limit that the box goes to infinity. What you can then write is you can write these states as if they were vectors in a Hilbert space. This is just a mathematical procedure. There's no mystery, no magic involved at all. We just say that these are vectors, and all these blobs here are orthogonal vectors. So this is very high dimensional vector space. It's called Hilbert space. That's where we do quantum mechanics. And in this Hilbert space, you can now formulate the evolution in terms of an evolution operator. This is an operator, but if the system is deterministic, this operator only contains zeros and ones. So U is 0 if it doesn't go to that state, U is 1 if it does go to that state. So you have ones and zeros, and that's a matrix you can write down. And all you have to do next is diagonalize the matrix, which enables you to write down a Hamiltonian operator, H. H is just the logarithm with an I in there. So it's actually an arctangent of U. And so you solve this equation U. And then lo and behold, if you write down this equation, this is the Schrödinger equation. So people say, what? You have a deterministic theory and you have a Schrödinger equation? What? Something is crazy in here. It shouldn't be right. Well, but look at these equations. There's nothing mysterious about these equations. Actually, to do the calculation, you have to do a little bit of mathematics, but the mathematics is very simple. You have to do the Fourier transform. So take these, here you see 11 states. In reality, it's much more than 11, but never mind, you can do the same calculation. This number is n, and you take these complex, these imaginary exponents as the Fourier kernels, and this is basically a discrete Fourier transformation. You can get the states, the energy eigenstates n, you can get by Fourier transforming the ontological states k. You can do this backwards. You can find the ontological states by Fourier transforming backwards from the energy eigenstates. The only difference there is a minus sign in the exponent. This is a very simple calculation, and it's very difficult to say it's wrong. No, it's just calculation. This is the model. This is what you have to do when you encounter a system, a part of the universe. This Hamiltonian H, however, in one way does not agree with the usual Schrödinger equation. So it's important to see where things threaten to go wrong, because this Hamiltonian H has as its energy eigenstates 2 pi over n. There's a delta t, which is a time step, times an integer, which means that the energy eigenstates of this Hamiltonian are equally spaced, more or less like in a harmonic oscillator, where they're also equally spaced. So this could be describing actually a quantum harmonic oscillator. Mathematically, this thing doesn't differ at all from the quantum oscillator, except that in the oscillator, this chain goes to infinity. But that happens if I put more states in between. But that's just a way of talking about how the universe evolves. So this actually happens to become the deterministic underlying theory of a quantum harmonic oscillator. So if you don't like it, you don't like it, but this is just mathematics. So quantum mechanics was thought to require a complete revision of logic. My claim is that's not so. What's not logical about this? In fact, mathematicians use vector representations a lot. If you want to know properties of the permutation group, what are the subgroups of a permutation group, it's very efficient to apply the mathematics of the vector representation. So given an initial state, psi at 0, then you'll find that, given the initial state as a delta peak, you say, yeah, I'm sure I'm in position x equals x naught. I have no doubt about it. So this is a delta function, a Kronecker delta, because I'm looking at discrete things. Then the vector function, this psi here, will keep the same form, but after k steps, it will not be x0, it will be the kth state. It can be in x of t. But the wave function keeps its delta form. Now, maybe you can say, yes, but in practice, I have probabilities. That's because you don't know the initial state. And the answer to that is that you just have to take a more smoothed out wave function. If you smoothen it, you'll get many, many different equations, but you can interpret those as probabilities. You just take the squares of these coefficients. They can act as models for probabilities just because probabilities are never below zero. They're never negative. So you better take a square. So this sounds idiotic, right? This sounds like a poor excuse for writing down Born's rule about probabilities. But I don't care whether you don't like it or not. It just works in practice very perfectly. So, but there are some relevant questions. Can you classically a classically evolving system only can you solve a classical system where the Schrödinger equation smears the wave function? Because that seems to be what you can't do. The wave function remains delta peaked forever, according to this. Now, in the real world, we think that wave functions smear. Where does a smearing come from? Can we make a model which do that right? Well, if you look at this here, you say, no, this is not the quantum theory because the wave function refuses to spread. Whereas, you know, for even the simplest particles, wave functions tend to spread out. How can we get that situation? And my claim is, yes, I can make such a model without losing the concept of locality or anything like that. And it goes as follows. I'm going to take a theory which I want to mimic, like a particle on a grid or something like that. And I add a super fast moving extra variable. That could be the hidden variable, actually. It's exactly what Bell wanted and didn't get out of his equations. The super fast hidden variable, which goes around like this. And it can take particular positions at some point, but it goes fast. It goes around so fast that this period is so short, it's even shorter than the inverse of a TeV of the biggest accelerator that we have, the LHC. So it rotates faster than even a single particle in the LHC. So this, because it rotates so fast, the energy eigenstates are discrete, but they're very wide separated. So the energy is extremely high. Even the first energy excitation is very high, like a super heavy particle that has not yet been detected by the LHC because it's too heavy. The slow theory that I'm looking at may have energy levels like this. Now I draw them here at not equal spacing. So the question is, can you make that? Or I'll explain how this can come about. But first I combine the slow and the fast system to just say that the complete energy spectrum of the system can look like something like this, that you have a repetition of the slow spectrum where the energies are only very close together, and it's repeated in the same sequence as the fast variable. So this is a total spectrum. I want to see, can I get this out of a deterministic model? At first sight, you would say no, but now I'm going to make a little trick, which is very important, that I can now try to make a model which generates any Hamiltonian I like. So think you have your favorite quantum theory, whatever it is. It could be the complete standard model. It could be a particle in a box or whatever. It has a Hamiltonian, and Hamiltonian contains terms where it has off-diagonal components. Having off-diagonal components is what makes this thing typically quantum mechanical. But if you encounter such a term in your Hamiltonian, if you apply that in your evolution operator, it causes a flip-flop. So this is the operator which flips states 1 into state 2, and it flips state 2 into state 1. A very elementary classical process. So this is indeed a component that you can add in a classical theory. But not in Hamiltonian I want, because in Hamiltonian I want the time scale is much, much slower than that of the fast variable. So the fast variable will make this flip-flop much faster than what you see in ordinary quantum experiments. So I want to multiply this matrix with a very small coefficient. How do I do that? Well, the answer to that is very easy. I take my fast variable. It is too fast to follow this. So what I'm going to do now is I'm going to use quantum language to solve this situation. And the quantum language tells you that I have to take the expectation value of this operator, which has a very large coefficient in front here, but I take the lowest energy eigenstate of the fast variable. The fast variable can be excited, but it takes so much energy to excite it. In practice, that won't happen. In the LHC, the grand unified particles have far too much energy to be produced in the LHC. So all you have to do is take the zero energy solution of that field theory. That field theory has too high energies to ever excite any of its excited modes, which means the fast variable will be in its lowest energy mode. And that lowest energy mode is a quantum superposition of its ontological states. So quantum mechanics comes in via the back door in this theory. When you compute the effective Hamiltonian this way, you find it is again this flip operator, but multiplied by number of ways in which you can generate that flip, divided by the number of states you have in this very fast variable. So now you get a number n1 over n2, which can become as small as you want. And now I can do this for all the states in the Hamiltonian, and now I can generate any Hamiltonian I like using this procedure. What I'm actually doing is I'm generating a system with interactions, and in the very end you can make a 1 over n2 expansion. And that generates eigenvalues which in that description are no longer equal separated. How can that be squared to what I said previously? I said all the deterministic models have equally separated energy modes. Yes, but you have many of these modes, many of these energy states shrunk together, put together into one energy spectrum. That makes things much, much more complicated in practice, so that indeed the energy spectrum I showed can be produced by this procedure. And the question now is, isn't this too good to be true? The answer is yes, there is a catch. The catch is, to make this procedure work, we first have to identify the so-called ontological states, what can be the physical real states in nature can be in, and then you have to set up this Hamiltonian with the fast variables. You have to make the fast variables choose between the states, and now you can set up your model. This means that in a Bell experiment, when Ellis and Bob want to change the setting of their apparatus, that change will have to be done first, and then you have to set up how the change is realized by these fast variables. But that means that the process of changing the settings by Ellis and Bob is a counterfactual change in the system. And philosophers agree, if you do things counterfactually, then you can get around the problem of the paradoxes that Bell and others encountered. My claim is you do not get that paradox if you assume that everything is deterministic. So now if your initial state is a delta peak, then you can calculate the probabilities. There's no paradox yet. The paradox only comes if the observers change their minds as to what will happen next. I have to, my time is running fast, so I'm going to skip some of my arguments. I want now to go to the second part of my talk, which is now make a model, not only of a single periodic system in the universe, but now try to be more ambitious and take a model that looks like the entire universe. The entire universe looks a little bit like what is called a cellular automaton. A cellular automaton is a grid. Well, the grid is supposed to be so fine that we don't see it with our present experiments. It is grid length is much smaller than the inverse of the highest frequency you can generate at the LHC. So you have no problem with things being in the grid. Every cell of the grid is in a different state. And there's an evolution law that says how these cells evolve in time. If I make one step in time, every cell looks at its direct neighbors and then updates its contents. And on it goes. This is a cellular automaton. It is completely classical. You might want to write a quantum cellular automaton, but that's not what I'm doing. I'm taking a standard classical cellular automaton. And now I apply this knowledge that I've just gained by writing down classical models to turn them to something that looks like quantum mechanical. So what I want to do is generate quantum fields with this automaton. And there seems to be no problem with locality because I can take a fast variable in every cell that's completely local. And this way I can make all the interactions among neighboring cells completely local. So at the level of the original deterministic model, there is no non-locality at all. So we have no problem with locality, nor do you have a problem with conspiracy. Bell was worried about the future determining the past, that violates the idea that the past doesn't know about the future. But that we don't have here. The cellular automaton doesn't know anything what it's doing, it just evolves. And this works very well. So the conjecture now is that we can now look at the symmetries of the standard model and then say, let's see if we can find back those symmetries in the cellular automaton. The claim is that is a way to find out which cellular automaton would possibly generate a standard model. This is a very difficult question, and no one has even started in trying to address that question. I've looked briefly at that question and found that the first thing we want to establish is find the symmetry properties. See if the standard model obeys the right symmetries and that those symmetries are reproduced in the cellular automaton. And then if you have then you can produce quantum mechanics by writing down the vector representation of that automaton. So every state the automaton can be in is a basis element of a Hilbert space. And all I'm saying, these basis elements evolve to themselves according to the rule of Schrödinger equation. Then if you have a fast variable, the fast variable should come into a fast variable state. And this state is a superposition. And, oh no. So the one remarkable thing about this is that, yes, the most features of the standard model are too complicated. For instance, the standard model has local gauge symmetry, U1, cos SU2, cos SU3. In principle, you can make a discrete version of that and put it on a cellular automaton. So yes, we can still manage that on a cellular automaton, but the more difficult part is gravity. How do we get the cellular automaton that obeys some sort of diffeomorphism invariance that the gravity theory seems to have? It's a central issue, central point of Einstein's general relativity. That turns out to be very hard. So I haven't even started in trying to address that problem, how to reconcile this is the general invariance. That I can't do, but there's another thing very interesting. The standard model contains one particle that has been very mysterious and has been recently discovered, the Higgs particle. What is peculiar about the Higgs particle is something it has in common with the cosmological constant. It is much too light. Its mass is 10 to the minus 17 at the Planck scale. How can that be? Where does such a small number come from in any physical theory? Can you write down a cellular automaton that naturally generates numbers like 10 to the minus 17? That's going to be hard. However, it will be possible. And that is because people have done some calculation with the Higgs particle that is very striking. They asked, what does the Higgs particle look like when you scale the description of the theory all the way to the Planck scale? And the answer is, a miracle happens. So there's something that you have to be very astonished about. And we don't want, I said, I don't want miracles. The miracle that happens is that the mass then looks very small, 10 to the minus 17, that's fine, that's not a miracle. But also its self-interaction, which most people would expect to go to infinity very quickly. Actually, the self-interaction goes to 0 too. This was not expected. If the self-interaction goes to 0, it might even continue to go to a negative value. And that would be problematic, because if lambda would be negative, the whole universe would destabilize, and there is a big problem there. And the LHC showed that the mass of the Higgs that we have now is very close to this unstable domain of the universe. But we don't know for sure yet, because the Planck scale is so far away, we don't actually know what sits in between. But we do know that this m becomes 10 to the minus 17. But there's something else which is well known in the physics of elementary particles. If you have a symmetry like this, which dictates the mass of a particle to be very small, the symmetry is well known. It's called Goldstone's symmetry. The Goldstone symmetry here is that you add a constant, which is the same constant everywhere. You add it to the field phi, the Hamiltonian doesn't change. So the Hamiltonian is invariant under a switch where phi gets a constant added. Now, this sounds very strange for a particle physicist, because this Higgs is not just a scalar field. It's a isospinner. It has 4 real components, forming an internal 4 vector in the theory. 3 of the 4 components are controlled by the SU2 cos U1 component of the gauge group of the theory. And that is a very complicated symmetry. And whereas phi, well, the Higgs field is just essentially just a single component particle, which corresponds to the length of the phi field. So what you have to do now is write this phi as a coefficient times a U object. This U is just a spinner with fixed length, unimodular spinner. So it's modulus times a unimodular thing. Then you find that the Goldstone symmetry acts on the R, the SU2 cos U1 symmetry acts on the U, and they don't talk to each other. R and U are 2 different things. So if you take that into account, you find that the Goldstone symmetry is quite easy to understand in this model. But now we have to find a cellular automaton that has a property that it has a very nearly perfect symmetry of this sort. There's a variable to which you can add a constant, and adding a constant to that variable changes the evolution laws by only 1 part in 10 to the, probably minus 1 part in 10 to the 34, the square of 10 to the 17. So there is an interaction in a cellular automaton which only in 10 to the minus 34 cases of all the possible states of the automaton, this field does something else than what you would have expected from its symmetries. So we know something about the standard model that we can derive. We know something about the cellular automaton of the standard model by plugging in something that we know from the standard model. So we have already a connection between the physics of cellular automata and the physics of the standard model. Let's try to proceed from that point. That's a very tough thing to do, but in principle, we can do that. So, so can we do this in terms of the cellular automaton? Well, I reached the conclusion of my talk, which is that what has been proved in the past is that deterministic variables cannot be introduced in a world dominated by the Schrödinger equation, but only when you assume that the observers have some mysterious free will. I have not yet mentioned free will, but only if Bob and Ellis are allowed to do something which does not affect the past of their cellular automaton, only then you can get into a contradiction. But Bob and Ellis do not have that liberty, because Bob and Ellis are part of the universe. And only if you have some changes in the past, you can change the settings that Bob and Ellis have been choosing in their experiment. So if you do that, if you take that into account, the contradiction for the Bell experiment goes out of the way. So the rule is, if you believe in determinism, you have to believe in it all the way. And this is a very important conclusion of this work, that you can't have halfway determinism, but secretly also do quantum mechanics to calculate how things really work. No, you have to believe that the whole theory is entirely deterministic. Then the contradictions are removed. So this is a big departure, and I believe such departures will be necessary for us to make the next step in understanding the world of the particles. For instance, those neutrino oscillations that were described in the first talk are a very peculiar feature of the standard model. We do not know what drives the neutrinos to oscillate in this particular way. Well, it's some property of the cellular automaton where the cellular automaton describes neutrinos, that they have these features of making oscillations. But here it comes a very important, what I've magnified here is the most important part of my conclusion. Let's read that for a moment. The perturbation expansion for the standard model will be replaced by a 1/n expansion. That n was the n I derived previously to get real quantum mechanics out of a deterministic system. You have an interaction which only occurs 1 in n times, so that the expectation, the wave function of the ground state of the fast variable contains n states. Only if they are in one of these n states, an interaction can take place. So that gives you an effective interaction Hamiltonian that has a 1 over n in it. So now doing perturbation expansion, you do the expansion in terms of powers of 1 over n. And then you get the same perturbation expansion that people apply in quantum field theories. Does this expansion converge? No, probably not. Do we care about that? No, we don't, because the first n terms will converge, and that gives you already fantastic accuracies. So don't worry. But this might tell us something about things such as to find such a constant, e squared over 4 pi h bar c. That number is well known to be 1 over 137. Where does that 137 come from? Well, in some interactions it behaves 1 over 137, but at higher energies it behaves as a slightly larger number. So I'm not saying n must be 137, but n will be a discrete number. So not all values for find such a constant are allowed in these theories. That is new, because in the old electrodynamics theories, we didn't know what to find such a constant was. It could be anything, any option from a whole range of real numbers. Now I'm saying, no, it's not you can't choose any real number there. You must choose very special numbers controlled by an integer n. Presumably that integer is not so large, but that is something you can only derive by adding quantum gravity, and that's too much for me at this moment. So I do not know how to do that part of it right. So I reached the end of my talk. I hope there will be some discussions. Thank you very much.
Thank you very much, Professor Hooft. It is a really great, complete and comprehensive presentation. Fantastic, exciting presentation, I must say. Thank you very much. We are really amazing hearing you explaining us all around the standard model and all these complicated stuff around. Thank you very much. So now we open the floor for the question here in the chat. I have already some of them. I will begin with the question from Wissam. She is wailing if you could, Professor, to explain us or talk us about the violation of the unitarity when making measurements.
Is that the question? That was the question that Roger Penrose also asked. I don't care so much about measurement. If you have, imagine, well, a classical system such as the planets going around the sun. How do you measure whether the planets go around the sun? It doesn't have to be so that the measurement affects the planets going around the sun. The measurement is just quite besides the model. So when you have a model, even of small things, for instance, the chip of a laptop computer, do you actually measure all the time what happens in this chip? You may or you may not, but what you're really concerned about is whether the computer works. What does the computer do if I hit some keys? I don't care to hit keys now, my presentation will disappear. But if I hit the key, something happens. But do I really have to measure what happens inside those chips? We don't care about that. The model that you make of nature doesn't care about what you are measuring. This is, I think, a relic of previous centuries of science, that in the 20th century it was found that measurement is very important, but only because it's only important because people were thinking that things are real if you also if you don't measure them, and that may or may not be true, but the reality might be something else. So be very careful when you measure something. It doesn't mean that you're not allowed to measure anything, and also doesn't mean that that measuring apparatus should be something beyond physics. No, the Geiger counter, you ask how people at LHC do their measurements. They just make an apparatus which itself also consists of elementary particles. Exactly. And it obeys exactly the same laws as a standard model. So I don't see why, if your model is a believable model, why you should pay special attention to measurement if the model itself already describes to you what actually is happening, as people wanted quantum mechanics to do for years, and now you see there is a way of doing it.
Thank you very much, Professor. And then we move on to the second question from Omar, who is asking, how can one demand that the time evolution of our universe be unitar when measurement has such a dramatic consequence on the quantum state that is yet to be understood? This is the first part of the question. And he's continuing saying that measurement is part of the universe is not satisfactory. Otherwise, there would be no need for an explicit collapse postulate.
But to begin with the last thing, I don't believe in any collapse postulate. I think the correct answer is that the Schrödinger equation, which as I derived basically here, I showed that the Schrödinger equation is describing the classical evolution of the thing. There's nothing else describing it. And certainly, if your wave function started as a delta peak, it continues to be as a delta peak in the original deterministic description. But only if we apply a 1/n expansion, it looks at that in terms of those degrees of freedom, actually you have a spreading of the wave function, but that is because we haven't taken this fast variable into account fully. We have made an approximation. So when you do quantum mechanics, actually quantum mechanics is a way of doing approximation theories if you don't know how to solve the equations exactly. This cellular automaton, which I described, is so tremendously detailed that there's no hope of solving that equation exactly. It's non-linear, there's nothing, there's no way to simplify it. So it's horribly complicated. But what you can do is say that many variables will be too fast to be distinguishable. Let's assume that they spread over in a wave function, the zero energy mode. The concept of energy is essential. So zero energy stays zero energy. So don't worry that this fast variable will climb out of that mode. It won't, because it doesn't have the energy to get away from its zero energy mode. It'll stay there. But the zero energy mode now has can be in different states with certain superposition coefficients. Those are man-made. It just means that our understanding of nature is incomplete. Therefore, we encounter superpositions. But it does not mean that when you make a measurement, the wave function collapses. You can. It really means that we don't know the wave function. So we don't know when we, for instance, the LHC starts with particles in two beams like this, and they hit each other. The two beams are not the state that particles can be in. The particles can only be at one particular point. Yeah. Whereas if they're in a beam, they are an ion state of the momentum operator, not of the position operator. But that just means that my initial state is uncertain. The LHC people have no way of making their beams sharper than a needle or something, which is very sharp, but it's also very widely spread in terms of particles. So their beams contain lots and lots of uncertainties. Those uncertainties that you have in the past will reflect in the future. So imprecise in the past means imprecise in the future. But these particles mix. So some particles collide, some other particles do not collide. And the net result is that particles go in all directions in the final state. So the final state is a probabilistic mixture. When you measure something, doesn't that go back to the delta peak? Well, if you measure one of these particles, you have made a change in the past. Now in the past, you only looked at those particles which were actually going head on and hit each other and went like that. That means you've selected out one state out of the initial particles, which is very special. This is just a way to argue that uncertainty in the past means uncertainty in the future. If your theory is not infinitely precise, it's because you put in some assumptions which were not infinitely precise. So if you think of the theory back in the classical terms, which most of us have forgotten, and most of us are not older than 100 years to remember how classically people thought about physics. I think in classical physics, these questions were never raised. So you can ask the same questions in terms of probabilities rather than wave functions. But that's just squaring. That is not a big difference. So in terms of probabilities, people never ask, how come if you throw dice, that the probability suddenly collapses into the 3 6s which I get out of my dice I throw. How could it happen that the probability just jumped into that peak? Well, it didn't. But if I write down a probabilistic theory of throwing dice, I might get that my initial state is uncertain, and that uncertainty may have been very, very small, but it becomes big uncertainty by the time the dice show a certain outcome. Is that miraculous? Is it strange? No, not at all. In all the casinos on the world depend on that principle. They know what they are doing, and they don't have a difficulty with the collapsing of the wave function from someone throws dice. Who cares? And my attitude in quantum mechanics is now the same thing. That the difficulty of quantum mechanics was that we did not understand what was going on. Once you understand what's going on, the problem of the delta, the wave function collapse just disappears.
Thank you, Professor. We have another question which is maybe aligned with what's just last word. The question is very long, but I will pick up the key point here. The key point that the Mohammed is asking is what do you think? Do you think that the strength theory would stand for the next 50 years, or it will be developed or change completely to another level, maybe simple one, than the current approach?
Well, it's a little bit outside the main theme of my talk, but close enough. And I'm myself very much interested in the answer to this question, which of course I don't know. Maybe string theory will develop enormously and blossom and tell us much more things about the particles that we didn't know. That may well happen. But from my point of view, what I find more likely is that string theory isn't quite right, because string theory is one of those examples of theories where people believe a lot in magic. There's the ADS-CFT duality is to some extent based on magic, which of the kind which I don't like. People should do better than believing in magic. So I believe, first of all, string theory will blossom, but the word magic will slowly but surely disappear. They'll just tell us, this is what the theory says. This is what actually is happening. In string theory, it's very nice to speculate what's actually happening. The string theory looks like it's on a lattice. Actually, I can even compute the lattice length there. String theory suggests that the world lives on the lattice. And then on the lattice, it becomes deterministic. But string theorists themselves don't talk about it like that because they didn't think about determinism in their theory. But I think strings and deterministic is a very interesting combination that they should investigate further. But I also encountered string theory in a different way, which is in relation with black holes. So like Penrose, I've been looking at black holes, but in a very, very different way than normally people do. And I found that the mathematics of the black hole horizon is approaching in a remarkable way the mathematics of string theory. So what I believe is that actually we should reproduce string theory, but now as a theory not for strings as fundamental particles, but for things, fundamental particles living on the horizon of a black hole. So, and on the black hole, we encounter the same mathematics. So maybe string theory is right because its mathematics is right, but maybe string theory needs to be adjusted when you ask the question, what is it that string theory is really describing? I don't know what string theory really is describing. I think it looks very much like they might have it correct, that string theory is describing strings, but I think it could be also that string theories will describe horizons, or maybe both. The ideal solution will be describing both the horizon of a black hole and string-like particles, and maybe there'll be some unification between string theory, black hole physics, quantum gravity, and the whole lot. That would be the most positive, the most ideal way of things could develop. But I don't know what I can't see in the future so very well. My glasses are a little bit hazy in that respect. So that I can say.
Thank you. So I will pick up only one more question due to the time limitation. There is one question very peculiar is, could you comment, can we say gravity is space-time? This is the question. Can we say gravity is space-time?
Well, that is a little bit too telegrammatic to accept. String theory is a bit more than, gravity is a bit more than that. Gravity is a symmetry of space and time in particular diffeomorphism invariance. Gravity arises when you discover that you can use different sets of coordinates to describe space-time. That's diffeomorphism invariant. My belief is that ultimately everything will go down to become something of a sort of a lattice. So strengthening so quantum gravity is space-time, but discretized space-time. We should say that if you come closer, if 2 points come closer than the Planck length, then they cease to have their original meaning as points. You have to replace them by something else. Exactly how that goes, nobody knows. But I think if you look at the coarse-grained lattices and you take the continuum limit by looking at distance scales large compared to the lattice size, then you'll be back in the continuum. And that's what gravity is. What gravity as we see it today is that. But how that continuum can be understood as the continuum limit of something discrete is a very difficult, important question. I don't know how to answer that. I wish I could, but I think we should investigate this further. But one of my main themes, main mottos is investigate this, but try to make small steps. Don't try to solve the whole world in one step. That's not going to work because the universe is far too complex for that. So let's try to make small steps and see if we can understand better what we are doing. That's also what my talk was about. Small steps in quantum mechanics. I think looking at the periodic system is a small step to look at first and then ask more difficult questions. But for gravity and black holes, it's the same thing. I first ask the simplest question I can imagine, then go to the next question. But don't try to solve everything at once. That's not going to work.
I would like to ask you, Professor, I mean, the discovery of the Higgs boson in 2012 was closed the chapter of the Standard model, was an exciting discovery. Could you tell us, due to the light mass of the Higgs boson, what is the biggest question that this discovery opened to us?
Oh, there are too many big questions. And
the mass.
the biggest question is how to put all these things together. So exactly. What the past has shown very often that if people ask the question right, which is very difficult, you ask the right question and you manage to solve, right also means answerable. If you ask a question that nobody can answer, like does God exist? You say, well, no, I don't know, can't answer. But if you ask the question to say, how can this be compatible with that? Like the question I've been asking, how can black holes be compatible with particle physics? It's a smaller question, but you have to ask even smaller questions than that. You know, how does a particle behave on the horizon of a black hole? That's one of the questions one can ask. And then by gluing those questions together, you can get a grand picture. And an approach is successful if the grand picture just suddenly shows that questions are answered that you haven't yet thought about. This happened typically in the past when we came with the full theory of the weak interaction, people realized that's the answer to the question, where does mass come from? We never asked that question, actually. We didn't care. Mass was just determined in the equations. And then people say, yes, the Higgs particle causes mass. Now we know the answer to the question, where does mass come from? We should have asked that question earlier, but we didn't.
Yeah.
And this repeats itself many times in the history of science. Like Maxwell should have asked, can light and electromagnetism be unified? He didn't ask that question, but he got the equations, suddenly discovered that light obeys the same equations. So that showed that he was on the right track, and he discovered a marvelously new theory of electromechanics.
Thank you very much. We have Wissam raising her hand. Do you want to comment something before?
Hello, I've got a question to Professor Gerard Hooft, if you allow me, please.
Yeah,
yes.
Please. Because, yeah, okay, go ahead.
Okay, I would like a professor to comment on Stephen Wolfram's announcement about the fundamental theory of physics using cellular automaton and graph theory. He recently announced in 2020 that he come up with an idea like a unified field theory using cellular automaton and graph theory. Can you comment on that, please?
Yes, indeed. I have some friends who are computer scientists, and computer scientists say we already work with cellular automata. It's one way to deal with problems. Think of the climate problem and the weather problem. You can understand how the weather behaves by making little cells on the globe, on the planet Earth, and then solve the equations for each cell in succession. So they say cellular automata are fantastic for computers. It's also it's an ideal thing to program on a computer. So in fact, they noticed that sometimes the cellular automaton contains things that look like particles or molecules or objects. They have the gliders, which you see moving around on your screen when you solve these equations. So they say, isn't that a great way to think of elementary particles? My answer is yes, but what we know of the particles is too far away from what we know about cellular automata. So to join these pieces of knowledge together is very hard. I've been trying to make a first step in this talk, which is a very tiny first step. We say there's one aspect of the cellular automaton that I like, which is the standard model has a very light Higgs particle. How can we understand that particle in terms of a cellular automaton? And I found, yes, there's a symmetry on the cellular automaton, which is very slightly broken, which means that if I know how this object, how this glider moves, I know how that glider moves, and nearly always the answer is correct. But once out of 10 to the 34 cases, it doesn't work that way. So, so that is a small step, but to make a big step is very hard. So to say that a cellular automaton solves everything is a nice prediction, but it doesn't have much effect on what we do in physics. So we have to break our problem into smaller pieces. And that's what I would say to Steve Wolfram, to say you have to understand in small pieces, why does the world, why could the world possibly work like this automaton? Shouldn't you study the physics of elementary particles? Because those are the things you think you could compare. But that actually is very hard. The standard model, I don't know whether you ever studied it, details, but it's a pretty hard subject to study on a Saturday evening. So, so you first have to study that and then ask the question again. But don't ask the full question, which is too difficult, but ask little features where the whole physics or mathematics is simple enough to analyze, and maybe you can find an answer that helps you in making your next very tiny step.
Thank you very much, Professor. Thank you very much for this very, very nice answer. I did a great presentation. And thank you. So now we will move to the next speaker, who is, we are very pleased to welcome Professor.
Would be unshare your screen.
Oh yes, sir.
Yeah, yeah.
I'm trying to find out how that works.
Just
click on the red
new share. I can new share, but how can I unshare? New share.
Stop share. Stop
share.
Red icon. Yes. Thank you.
Okay. Thank you very much, Professor. So we will move on to our next speaker. We are very pleased to welcome and to have with us Professor Claudia Felser. She is a professor of physics and chemistry at the Planck Institute for Chemical Physics of Solid. Professor Felser was awarded the James C. Max Groddy Prize along with Bogdan and I for their big work on the theoretical prediction, design and realization of no-magnetic and magnetic topological semi-metal and the new type of topological insulator. So, and we are really very happy to have Professor Claudia with us, who has accepted our invitation, and she will talk us about the topology and chirality. So, Professor, the floor is yours. Thank you very much.
Yes, thank you very much for the very kind introduction. And I especially want to thank the Arab Physical Society to give me the honor to speak here. I am an experimentalist, first of all, and I think I'm strongly connected to the talks in the afternoon of Pablo Jarelio Herrero and Charlie Kane. So Charlie Kane, who is for sure the inventor of the topology, and I try to make a little bit the bridge also to the other speaker and show how we can do something in condensed matter physics, maybe to understand quantum equations in a kind or topology is a very nice new concept which enables us to even understand condensed matter newly. So this is what we call also a kind of revolution in condensed matter physics, and it started with if you can say, even with a quantum Hall effect from von Klitzing, but it really was boosted by Charlie Kane's and Mailer's prediction of the quantum spin Hall effect in graphene. So topology is a concept from mathematics and which deals with the surfaces of objects. So if we have this pancake here, for example, it's the same kind of surface like a dice, but there's a different surface if you have a hole in our pancakes, and in America we eat donuts, and but this has the same topology as a coffee pot. And the same you can continue with pretzels, which have 3 holes, etc. So this concept means in topology you can transform object which has the same topology into its another without any break using a scissor or something. So this can be then translated also to condensed matter physics. So and the whole story, as I said, was also awarded a Nobel Prize for the quantum anomalous Hall effect. And as I mentioned, Charlie Kane and Mailer. And this is really when it became a story of condensed matter physics and looking for materials, was when they predicted that we can find a quantum Hall effect, which was discovered in a complex 2-dimensional electron gas, even in a material like graphene, and based on the spin-orbit coupling. But you can imagine spin-orbit coupling is a relativistic effect, and graphene is made from carbon, it's light elements. So the effect was expected not so big in graphene. So then you can think, and now I come to condensed matter physics, and I want to say we all think about topology of the electronic structure. Here I simply want to say graphene is a material, and similar to other compounds, it has a valence band where we have electrons which are occupied and a conduction band which is unoccupied, and we have a band gap in between which separates the valence and the conduction band. And so the needs which you need if you want to find this topological material, so was predicted in this paper from Charlie Kane and Mailer, and I'm sure we will report about this. But as I said, the problem with carbon was that it's a light element, and another ingredient which we need is heavy elements. So in this sense, if we have here the energy gaps of semiconductors versus here, for example, the lattice constant, you see that there are also materials which have heavy elements, bismuth telluride, mercury selenide, and mercury telluride. And this were later considered, we cannot use an element like what would be very nice. Graphene is very simple. We might have to go with 2 elements and find other materials. So what are we looking for if we think we want to look for topological materials? What is the difference compared to a normal semiconductor like silicon, for example, where we have this valence band, conduction band, and band gap? So the difference is that the topology of the electronic structure is different, and this can also is shown here. So if we, for example, have the bonding strength in such a semiconductor is not so strong, we can also have a situation where there is an overlap between the valence and the conduction band. And this overlapping region makes this then more semi-metal, so it's not an insulator or a semiconductor like silicon or other semiconductors. So it's more semi-metal, but what can happen is here that these crossing points in the electronic structure are forbidden. So they can be lifted by symmetry or by topology, and in case of topological insulators, so we need spin-orbit coupling. As I said, relativistic effects become very important, and then we have a situation like this. So this crossing is forbidden, so it can be lifted, and then we end up again with the semiconductor. So from the first view, it looks the same. We have a valence band, conduction band. Okay, but now if we look more careful, we see that we have in the valence band a part of the conduction band and vice versa. And this is symbolized here by the topology, and very often people like to draw a donut for a normal semiconductor, which is called then also a trivial semiconductor, and a Möbius stripe for a topological inverted semiconductor because of this tiny bit of the conduction band in the valence band. And these two electronic structure are topological protected. So they are, you really need a scissor if you want to convert this ring into a Möbius stripe and re-glue then the ends of the ring. So if you look carefully, this has then also only one surface. So what does this mean for the material? And we make materials, we really make materials. So if I have a normal crystal, so this should be my crystal, for example. So if this crystal is an insulator, this means all the electrons are localized in the crystal, and the crystal, this is symbolized by, this is an insulating crystal, it's like a grain of salt, which you maybe have on your table, or like a piece of silicon. But the situation is different if we have here the topological electronic structure, because what is very unusual here, that now, because of this inversion of the band structure, the conduction band and the valence band are connected by surface state. So there is a so-called by boundary correspondence, and this surface state is here visualized by this blue and red line. So this is related with electrons, and these electrons have spin, and this is a topological surface state. So what is very special with the surface state, and this is because the inside of my crystal is topological protected. It has a different topologies than the outside. For example, it's vacuum, and therefore we have the singularity here at the surface. And here, these electrons on the surface state of this material cannot be destroyed. So if I would take a hammer or scratch the surface, I think this surface would go maybe a little bit more inside of the crystals, but they are really topologically protected. And this is really new, a new concept, and it might be very interesting for many applications. And I want to tell you a little bit more about this. So the very special thing is that my electrons are, there is a spin, you can maybe go back, and the momentum of the electrons here on the surface, and they are locked for the surface states, which means, so we have now electrons which are topologically protected. They have a direction, so momentum, and they cannot backscattered into the other direction because spin and momentum is locked. And this will lead to very interesting properties, because we can have this kind of electrons at the surface, but also in the bulk of my single crystals. So this is a key and important property of my topological materials. So now we have you see behind me a periodic table, and the periodic table was also mentioned by the last speaker. So now if you combine all the elements in the periodic table, and I'm a condensed matter physicist or solid state chemist, whatever you want, so I can make a lot of compounds, and so far it's around 200, there are 200,000 compounds known. In general, inorganic compounds, and for all these inorganic compounds, we already have determined whether they belong to one class, the trivial insulators, or the topological materials. And what was surprising as a study of all these materials is that there's a significant amount of materials which are topological. So if you see simply the poor compounds like they are made, it's more than 25% of the materials are topological. But as I said, and I will give you a little bit of taste, this might to new properties. This might to possibilities of new electronics. And in one question, people even asked the question for quantum computers, and words like Majorana fermions were mentioned. All these properties were not thought about before the invention or the prediction, the first prediction of topological materials. And now we see totally new properties and understand properties of materials very different by taking topology beyond simple crystal symmetries into account. Recently, we also started to work on magnetic materials. This is even interesting if one wants to take correlations into account. So what we do nowadays, so we have our periodic table here, and we click on the elements, and then on this website, and then we see immediately whether material is topological or not, whether it's interesting for us to work on, or whether we can expect new properties. This was the result of this very systematic investigation of all the materials on Earth. Okay, so what my title is not only about topology. So to make a bridge to all the other speakers eventually is also, I would like to mention that if my electron, in case of my electron spinor momentum is log, the electron is also chiral. And in condensed matter physics and solid-state chemistry, chirality is known in the real space. This is in the reciprocal space. In the real space, because, for example, we know that the carbon atom can have 4 ligands. And if I have 4 different ligands on a carbon atom, so I can make a chiral molecule. So then I have the situation where the molecule, the molecule and the mirror of the molecule can be not brought together like this. Is, I think there's something written here on the bottom of my slide, already was recognized by Lord Kelvin. So chirality is interesting in many different areas, and you will hear maybe also a little bit of chirality from graphene, but also this twisted graphene is, for example, very interesting, and this is speaker of the afternoon. The second one I want to mention here in my talk, Pablo. So you can even make giant chiral molecules like this graphene here. And then you have very interesting properties like what Pablo will probably talk about superconductivity and quantum effects. Anyway, chirality is but also known in high energy physics, and it was also slightly here mentioned by the other speakers. So the weak force is based on chirality. Here we have also parity violation. So here, in case of the beta decay of cobalt atoms, they were expected that the beta decay goes in the same direction if you build 2 coils which are like a mirror picture. And but the observation was different. This is also very interesting because even people think that there's a connection between the weak force. Eventually, there's a difference in molecules. So if we have these molecules, for example, the problem is that we cannot distinguish them. So one big thing is in organic chemistry, and the recent Nobel Prize was given to Ben Ellis for the synthesis only of one molecule which only has one handedness, and this is very difficult. So you only can do it with chiral catalysts because they have exactly the same energy, so it's very difficult to distinguish them. But there is a small difference in energy, and this is based on the weak force. So, and why are chiral molecules so important? This we know from biology, because we have right and left-handed DNA and also the sugars, but you are only existing from one DNA. And this is surprising if you take into account that the energy between the 2 molecules is exactly the same. How could nature at a certain point in history distinguish? And people think this is really important for the origin of life. So what we are doing is we are looking for chirality in also chirality. We combine a chirality of the electrons, but also of the solids. So we make chiral crystals. So this is also possible. It's as difficult as to distinguish 2 different chiral crystals, as difficult as chiral molecules. And there are also topological chiral molecules, and I want to talk a little bit about this. So making a connection between topology and chirality. So we can make chiral crystals here. For example, one crystal we can even make with a determined chirality. Even this happens sometimes like this, but sometimes like that. But we get poor crystals which have only one chirality, which is very good for our experiments. And these are 2 examples of what I'm talking about. So I am a solid state or condensed matter physicist working with crystals. So why the whole story? So the idea is here that at the beginning we have a Hamiltonian, and we have the same Hamiltonian as in high energy physics or in astrophysics. So we have the Dirac equations, Weyl equation you already heard about from Roger Penrose about Weyls. And I will talk about semi-metals crystals which have these Weyl properties. And what we do is then we grow these crystals and we investigate their properties, and we prove whether in these crystals we see that this equation really can be applied, and we see the results which theory predicts. And this is very nice in topology in general, because topology is a field for we experimentalists. We look for the papers in the morning, I always say, which theoreticians have written. And then we simply grow the crystals which correspond to the Hamiltonians, and then we investigate the properties. So, and here it really works very well, surprisingly, because this topology and the single particle picture is allowing prediction which were not possible before in condensed matter physics. So the things which we want to investigate here is, I already mentioned in my pre-words, one important thing is the so-called boundary corresponding, so that there is a special surface state related to the topological properties. But the other thing is also that we have this very special chiral electrons. And to make the connection to the Hamiltonian, for sure. So if you talk about Y physics during the Big Bang and the evolution of the universe, it's different from what we are seeing, because we are looking for electrons. We are looking for the properties of electrons which are dressed like these particles. We call it quasi-particles, but we see whether the power laws or the special properties really are valid if we do the corresponding experiments. And what we use is then external stimuli like temperature, electric field, magnetic field, pressure, and light matter interaction eventually to change or control the system. As I said, so we don't look for the real particle like the real hen. So our electrons are dressed like this particle, like Y. So we have massless electrons in this sense that in our electronic structure, we see really these cones, which you already have seen in Professor Penrose talk. And we look for these quasi-particles and look whether we can fulfill or investigate these properties. So, and now I come to the main part. So we really designed this certain electronic properties. And as I mentioned, so we can see interesting properties in the surface, but also in the volume of my crystals. Here you see my crystal, with this very interesting surface state. And I already explained to you. So we have this overlap between the conduction band and the valence band. And we can have spin orbit coupling, which opens up here now a new band gap. And these are the so-called topological insulators with the surface state, which I have shown also on the second slide. But there are other systems which now makes the connection to Penrose. So we can design materials which have these cones. So there can be Dirac cones or Y cones. So this is the case if we have certain symmetry in our crystals. So if our crystals have rotation symmetries, for example, then there are this connecting points here, these degenerated points are allowed and not forbidden. So it doesn't open up a full gap. So we keep these cones here at certain position in my material. And depending whether these cones are at high symmetric points or low symmetric points, I have Dirac or Y semimeters. And this is interesting because these cones are then the properties in the crystal. It's inside of my crystals. And the interesting thing is if I have these Y cones at low symmetry points, so I have points in my crystals in the electronic structure where the electrons, for which the electrons, the spin and the momentum is locked, and which are chiral. So we have different chirality for the 2 points in the reciprocal space in the electronic structure of my crystals, and these points are chiral. And then they behave like Y physics, so I can see experiments here which maybe are predicted for other system where one expects Y physics. And this is the interesting thing what we can do with solids. So one very interesting field is, and this is all about chirality, and I already mentioned even the parity violation of the weak force is, can we see broken symmetries in solids, in the quasi-particle of solids. And one really important topic or hot topic I can say, which were very interested, in which condensed matter physicists in this field were very much interested when this semi-metals were discovered, is the chiral anomaly. The chiral anomaly was originally formulated for the vacuum state and explaining eventually also the asymmetry between particle and antiparticle. And as I said, we could then translate this in a quasi-particle picture by addressing our electrons or our holes, which we have in semiconductors, electrons and holes, and eventually see this experiment here in a condensed matter system in a crystal. So, and this chiral anomaly is also an anomalous non-conservation of a chiral current. So you need the famous E dot B field. Here, I explain it later in a second, but the idea is that you can have a situation where you reach the asymmetry between elementary particle and antiparticle based on this chiral anomaly. And there was the question, can we realize this in a condensed matter system? And indeed, this is the case. So if we grow these wide semimetals, we look for certain properties, and one is the chiral anomaly. So this is a situation, as I said, if I have a magnetic field, and details written in these references. So if I have a magnetic field, so if I simply measure transport of the crystal, and I realize the situation that the magnetic field and the electric field are in parallel, what I do then with my Y points, I make an asymmetry here between the 2 points, these points of this Y points in this material, and the consequence would be a negative magnetoresistance effect. This was predicted by theory, but we can have also a thermal version of this by adding on top to the magnetic field and the transport measurement a thermal gradient. So I would generate a difference here based on the thermal properties, based on the entropy of the system, and this was predicted by some theoretician. Even string theory was mentioned, like an axial gravitational anomaly, which is again only in a kind of quasi-particle excitation, but certain observable was then were predicted. On top, what we always do if we want to see whether we really have a Y semi-metal, so as I mentioned, so we have these 2 Y points which act like magnetic monopoles in the bulk of my single crystals, but we also have for the Y points very signatures in the surface state, and the surface state of a Y semi-metal is simply an arc, so it's not really a closed surface state, what we normally expect, an arc between the 2 Y points, which are connecting the 2 sides of the crystals. So in general, it was also predicted that if we can design materials which have this property, that we see giant responses to external stimuli, which was not observed before, but for which we are looking now. So we have this, in this sense, a list of properties which we would investigate if we find the right material, which exactly is designed in this way that we see an electronic structure like this. And indeed, this was possible. So, and first predicted by theory by 2 groups from Princeton at the same time in a simple class of materials. It's a binary compound made by 2 elements, and the crystals are quite beautiful. You can grow them by chemical vapor transport, and we simply investigated here the properties which were predicted. So the first thing was this giant responses. So what we did, simply measure the resistance as a function of temperature. And what you see here is the resistance without a magnetic field. This you could do in a simple measurement by making contacts at the end of the crystal. And what is interesting, all these topological materials, or especially also these Y points, we can grow them at extremely high quality, show these wiggles here at the end. And first you could think it's noise, no, but these are quantum oscillation. So this even let us exactly describe the electronic structure of this material. So this show very beautiful quantum oscillation. And then they behave like a semi-metal, because these connected points doesn't open, these compounds have not a full gap like a semiconductor. So if the resistance becomes smaller, it's very typical for the semi-metal. But what happens if I apply magnetic field, and these are fields which you can realize simply in the lab, you make this compound at the end an insulator. So this is very typical, that you can transfer this semi-metal into an insulator, so you get a topological kind of insulating behavior, which has here the plateau, and the plateau is based that the surface state, the topological surface state, never disappears. So this was the first thing which we could observe, and this was very good. And then we looked for the electronic structure, and I told you that this is like what was discussed already in Professor Penrose's talk. So if you have this linear dispersion of the bands, so this quasi-particle have at the end no mass. So we have to look whether we see this linear dispersion in these materials, and you see this material shows nicely the linear dispersion, and you see there is sometimes a splitting of the band, which is based on the spin-orbit coupling. And since we make this materials heavier and heavier because we take elements from the bottom of the periodic table, so we like the bottom of the periodic table because relativistic effects become very important, and we think this is the more interesting part. So we see then that the splitting based on the spin-orbit coupling becomes larger. So in the next step, we look for the surface state, and this are here calculated values for the surface state, and this here are the measured values of the surface state, and these are simply points which are drawn to guide as a guide for the eyes. So where the Y point should be, and you see really that you see a good agreement between the calculation and the measurement. So then we wanted to investigate the chiral anomaly. For this, we had to make this nano ribbons because there was a lot of, you must make sure that you don't have artifacts in the measurement. So we simply made nano ribbons out of our nice single crystals. And so we doped it a little bit with gallium. This happens when during the processing of this material. And here are the measurements. So we did measurements. In one case, we measured the magnetic field perpendicular to the current, and then we measured the magnetic field in parallel to the current. So if we measure the magnetic field perpendicular, it's a normal Hall measurement. But for the proof of the chiral anomaly, we have to measure it in parallel. And here are the Hall measurements. So again, here at different temperature in a magnetic field, you see again the nice wiggles here. And this is very nice because thanks to this quantum oscillation, we can exactly say where is our energy until which the electrons are filled in the electronic structure, and are the Y points really there where they should be, close to the Fermi energy, so that we see the property in transport. And indeed, from these wiggles, we could see that the Y points are where we want them, and we see a nice positive magnetoresistance in the Hall measurement, which is quite high. So in the moment when we then go with the field and the magnetic field and the current in parallel, we see what was predicted by theory. We see this negative magnetoresistance effect even up to room temperature, the so-called signature of the chiral anomaly. Okay, in the second step, then we try to realize this thermal chiral anomaly, which was claimed to be the axial proof for the axial gravitational anomalies. This prediction was done by Subir Sachdev, a theoretician from Harvard, and his group by string theory, but also made by some of the astrophysicists, that you can do this. And the prediction here was, you should see, if you measure the thermal conductance in this material, you should see a B-square behavior at very low fields, which then turns around and goes to zero. And we were really surprised, and this is a nice thing of topology all the time. It's surprising how nicely theory here works and how you can realize this in real material. So this was then later also redone by other groups, so we could show the chiral anomaly and the gravitational anomaly in a few other materials. But recently also people here, like Jos Herremann's group, they did it even a simple bismuth. They make very clean bismuth doped with a little bit of antimony to get a very nice band structure, which I have shown you, the Y band structure. And here they see also the axial the chiral anomaly and the gravitational anomaly, which shows that in solids, in quasi-particles, we can see this fundamental broken symmetry. Anyway, it's interesting to see it maybe for matter and antimatter, and other experiments are probably planned in CERN and so on to see it with the real particles. Okay, anyway, it's this nice experiment, and this was also because we did it in collaboration with IBM, made it even to the New York Times. Okay, so then there was another prediction, and this is based off work of Xu Shenzhang, also again, the others, and here also of, for sure, Frank Wilczek. So he predicted that there should be an axion particle in corresponding to the dark matter. And this was also related to charge parity symmetry problem. And here, this is a prediction of then the translation again into this condensed matter system. So Shushen Zhang and co-workers, they said you should find a material where you have a charge density wave, which opens up a band gap, so an insulating compound. Then you could see evidence for an axion fason in this material. So we had an idea about the material because when here is now a band structure, which the condensed matter physicist and me like. So this is the electronic structure now in reality for this material, which is chiral. You saw already the crystals. So it's even chiral. And so we saw this is a really nice material because it has this very nice linear dispersion, which goes with zero mass. At the Fermi energy, where you separate occupied from unoccupied states, and so on. But then if you look in photoemission, where we can see then the real band structure in the crystal, we see that we have, here's a zero. We see that the linear dispersion doesn't go really to zero. And this agrees also with the electronic structure. We saw that this material has a band gap and a so-called charge density wave. So this we recognized as really the system which was predicted here by theory in 2013. And you see our experiment came later, and where you had exactly the situation. So you have this y points in the real space, but what happens then, the system, because doesn't like the situation, so it develops a charge distribution in the crystal. The atoms stay where they are, but the electrons, they redistribute in the crystal to open up this band gap. And therefore, what we saw in this material, without any external forces, it's an insulator. So it's not showing the electronic structure, which was here predicted by theory. It shows a different electronic structure, which looks like more like this. And this is what one expects also for a correlated system and for this axion insulator. So there was a question, how can we drive the system back? Can we convince our crystals to go back? And there are different ways. One here was the experiment with Johannes, so you can put pressure on the system, then you also close the gap and you drive it back into the white semi-metal. But what you can also do is you can again apply an electric field and a magnetic field. And what we wanted to show is like first applying an electric field and driving the system back, and then showing that we have the chiral anomaly by applying a magnetic field in parallel. And what we saw is that if we apply the magnetic field perpendicular to the current in our system, then we don't see no effect. But if we do it again, like in the chiral anomaly, to have current and field parallel, we see the so-called negative magnetoresistance. So we think this is an evidence for this axion fason, but we are now looking for other systems because it might be more common that there might be another material out there for sure, maybe even a magnetic material where we can show it. So the point was also to show now there's one condition, and this is more for the expert, was that the nesting vector of the charge density between the white points should be corresponding to the distance of the white points, and this was not so easy to investigate, but the synchrotron radiation, we could see this superstructure reflection of the material, which has proven then that this is exactly the case. Okay, so I want to come now to the second part of the talk where we wanted to go beyond. So as I said, we had this white point, this Dirac point, but we also thought there must be new fermions maybe beyond what is known in astrophysics and high energy physics. Maybe we can go and eventually, especially because if we have chiral crystal structure, even more interesting properties can be realized in this material. And in case of chiral structure, it would be also nice then to have crystals which have one enantiomer and the other enantiomer. So can we make the bridge from chiral electrons to chiral real space? This was the idea, even by having these new fermions. And this paper also has gotten some attention because the idea was, so Benacker, who seems to be the referee of the paper, of our paper, reminded that Heisenberg already thought it's maybe nice if you could make a lattice on the universe, maybe then you could even find new particles which goes beyond what is known in high energy physics and astrophysics. And this was the idea, to do this new fermions. And here we wanted to combine interesting properties which we already know from chiral crystals. They show interesting optical properties from topological semi-metals, and what can you do then if you do this new kind of fermions. And the big interesting thing was here that this is again our crystal and this is our surface, so that we now have these points which act like monopoles at different energies in the electronic structure, which makes them also very special in the properties which we can observe. And on top, we have now this Fermi arcs which go all over the surface of the reciprocal space, I have to say, because we always look in momentum space and real space. So this is a momentum space because we look here for the electronic structure. So there was an expectation that we can make very new, interesting things. So luckily we could, again, grow these crystals, and here we could even grow crystals which are having the poor handedness, so we can really distinguish the right and the left hand crystals here, because we can make both, which you see here in the X-ray, where you see really the handedness, but there are other ways also to prove the handedness of this material. So the interesting thing is like in the molecules, so they have exactly the same electronic structure. You remember I showed you also some band structure, some electronic structure. And here, if you have one handedness or the other handedness, they look exactly the same. Even the crystal structure has different handedness here. So this is also the reason why they are energetically the same, and why it's so difficult also, for example, for pharmaceutical industry to separate different chiral molecules, and we have the same situation here in solid. But the advantage compared to molecules which we have here is, if we then apply now the concept of topology, we recognize that the chirality of these degenerated points are different. So there is a difference between the two electronic structure. So can we see this? Can we prove this? And maybe in the future, can we take advantage of this to fundamentally break symmetries, maybe even to separate different chiralities of molecules, or so and so on. So these 2 points are more degenerated. So these Y points were 4 times degenerated, the Dirac 2 times degenerated, the Dirac points were 4 times. Here we have even a 6-fold degenerated point, and the air point, you see here are many bands coming to the same point. And here we have a 4-fold degenerated point, like a Y point, but it looks a little bit different if you do this 3-dimensional drawings. But you see you have linear dispersion, which has leads to massless states, and this are going beyond what we know from Dirac. And the topological charge in these materials are also higher than what we know from the normal topological materials here. But anyway, because we have now 2 different chiralities, we might see even different signs of the topological charge. This is more for the experts, sorry. But you see now, if we again do photo emission, we can see exactly the band structure, and we can show that the material really has the band structures we have expected. And now in the next step, we can also look whether we get this giant surface state, and for the both crystals, we have this find this giant surface state, and they really are also chiral. So even if the electronic structure is exactly the same and we cannot distinguish, the interesting thing is that the surface state are chiral. So they are really distinguished for each of the chiral crystals, which I think, as an experimentalist and having even interest in chemistry, already tells me something very nice, because if many experiments which I can do at the surface, for example, catalysis, might be now I might be able to break the symmetry in these materials, because we can have different chirality of the crystals and they will have different chirality of the surface state. Anyways, this you can see even for other systems and other scientists like Hassan's group, also with whom we really like very much to work also together, showed this for other crystals of us. It's really not something, it's very general in this class of materials. I don't want to talk too much about it this year. It's maybe because the time is running. So we have here, we can here really see now also this, the next thing was to investigate here this Chern numbers and the sign, and thanks to this large spin orbit coupling, we could even show in the science paper that we really could show this large Chern numbers, and also that different crystals with different chiralities have different signs of the Chern number. So also here we see a distinction which we don't see in the molecule, but the electronic structure is simply the same. Okay, you see here also nicely, again, the chirality in an STM experiment. And anyway, since I have not so much time and I'm running out of time, I simply want to show that we simply thought also whether we can use this for catalysis. And indeed, we did some catalysis experiments on this material, and simply to make the bridge a little bit wider. And we did first hydrogen evolution reaction on this to prove or to learn how to do catalysis, honestly. And we saw that this material are superb catalysis because of this very special electronic structure. And in the next step, we wanted also to see, can we make maybe a bridge between this fundamental broken symmetry in chiral molecules and the chiral electrons, which we are interested in. And indeed, what we saw, we tried to do absorption on this chiral crystals, and we saw an asymmetry between the absorption. So it makes really a distinction whether we have left-handed molecules or right-handed molecules on these absorbed on these crystals. So maybe it's a way to bridge between chiral electrons and chiral quasi-particles up to chiral molecules. So this is a little bit our big vision. Okay, in this sense, we plan now also with the chemist, and here is Ben List, who collaborates on some issues with us to make the bridge between chiral molecules and chiral topology in condensed matter systems. I only want to give you now a taste. I cannot go into details. And with this, I come to the summary and the vision. It's more vision. So I simply think, I hope I gave you a little bit the idea of topology. You will hear more from other speakers in the afternoon, but I wanted to bridge it to fundamental broken symmetries. And I used chirality as one thing. And I think it's still, I recognize that there are a lot of open questions and very nice areas of research in condensed matter system, where you even can learn a lot beyond condensed matter systems. And I think one can even go in direction, maybe making bridge between chiral electrons and chiral real space systems like molecules. And maybe in the future, you can even add magnetism, correlation, and superconductivity to chirality, and also investigate fundamental interesting physics in this systems. I thank you for your attention, and I'm happy to answer questions.
Thank you very much, Professor, for this great presentation. Thank you very much. So since we are really late from our scheduler, I will pick up only, I'm sorry for all the questions that are listed in the chat, but I will pick up only a couple of them, which is really connected to the, directly connected to the talk. So the first question is, are topological effects only restricted to the surface of the crystals?
Yeah, a little bit. I wanted to show also in my talk. The second part was like with the chiral anomaly. It's a bike property. It's not a surface property. So it's really to the bike. So the broken symmetry which you see, and I think there's more to come. I think more prediction even which are really related to the bike. I had not the time, but we see giant Nernst effects which are going beyond whatever was predicted before, even in systems like antiferromagnet, where you didn't expect these properties in the bike. So for energy conversion, you can see effect. I think there's still a box of Pandora to open a positive sense, many interesting properties which can come in the future. of bike properties of these crystals.
Thank you very much. There is another one, I believe, that is, are these advanced techniques useful in making high efficiency solar cells, given that there is an integration between this technology and solar cells using nanotechnology?
I think there are prediction. I would say I think there are already prediction and effects shown that you can go back to the simple solar cells, so you don't have to have complex systems like you have. So this galvanic effect and and higher order photovoltaic effects, which are simply now giant because they are so enhanced compared what one has expected for normal semiconductors, that this might be interesting. I think there are nice predictions for Naoto Nagosa and also for my group. But I think there's not so much done yet, but I think this is still a field to explore to maybe find solar cells. And the question is here, whether the new solar cells, the hybrid the perovskite solar cells, which have heavy elements, how much topology is here at work, you know?
Thank you. The last one, maybe this is the last that I will pick up here, is Gerard anomaly robust against disorders.
So how the question, how to robust is the chiral anomaly against disorders? This is a very good question, and it still has to be investigated. So far, you need the Y points at the Fermi energy, but I know somebody who wants to now investigate even amorphous system. For application, it's much easier if you can find the effects even in amorphous system. I think the important thing is this general properties of the electronic structure. The question is, do we really need the translation symmetry in a condensed matter system? Maybe not. My intuition would be no. So, and there are already one theory paper saying you can use amorphous systems. So if you can then use amorphous systems, it should be stable against disorder. Thank you for this very good question.
Thank you very much, Professor. Thank you very much. Yeah, really, we are very happy with your answer, with your talk. So now, as I said before, we are really very late. We move to take the 50-minute break, and then we will reconvene in the next session. Thank you very much.
Yeah, thank you very much. Also, thank you very much.
Thank you. 50 minutes break.
15 minutes.
15, yes, sure, 15. 15 minutes, sure. No, 50, 15.
15.
Exactly. 1-5. It is not 5-0. Thank you, Ammar.
Thank you. Thank you.
Very nice session. Thank you very much.
Thank you.
Assalamu alaikum. Can you hear me?
Yes, yes, yes. We've been looking for you, Professor. Good afternoon.
Yes, we hear you, Professor Ellis. How are you?
I'm fine, thank you. How are you?
Yeah, I'm fine. We'll start within minutes. Yeah.
Okay, so I'll be ready. So can you still hear me okay?
Yes.
Now I can't hear you. Could you say something, please?
Yeah. Yes. Do you hear me?
Can't hear anything.
Dr. Shokh, do you hear me?
Yes, of course, I hear
you. Maybe you have problem with your speakers. Just enable audio.
Okay.
We are hearing you well.
Yeah, there's something wrong with my earphones, but it's okay. I switched back to my laptop mic. It's okay.
Okay.
So do you want me to share my slides already or wait for a bit?
Yeah, if you like, you can just use the share screen, yeah.
Okay. Just a second.
Okay, Professor Ammar, shall I introduce him?
Yeah, please.
Good afternoon, Professor Ellis. I think we met before at University of Bahrain some 13 years ago.
Right.
It was a great pleasure to have you with us today in this inaugural event. Now, John Ellis is a theoretical physicist who is currently Clerk Maxwell Professor of Theoretical Physics at King's College London. Ellis' research interests focus on the phenomenological aspect of particle physics, and he made important contributions to astrophysics, cosmology, and quantum gravity. He received Dirac Award and several prizes from the Gravity Research Foundation. Professor John Ellis, it gives us great pleasure to have you with us in this inaugural event to give a talk titled "Which Way Beyond the Standard Model of Particle Physics?" And the floor is yours.
Okay, well, thank you very much for your introduction, and thank you for the kind invitation to talk at this inaugural meeting. So I congratulate you on both holding the meeting and, of course, also starting the Arab Physics Society. And I'm just sorry that I can't be with you in person on this occasion, but I hope to meet up again in person in the near future. So I'm going to be talking about a topic which is somewhat different from the previous speakers, in some sense, somewhere in between condensed matter physics and gravity, namely the standard model of particle physics. And I'll be trying to refer back to some of the previous talks on occasion. In particular, I was very impressed at the end of the previous speaker's talk when she showed her research group, and there was a guy in the picture on the left-hand side who looked just exactly like me, but I can assure you it wasn't me. Anyway, so I'm going to start off by talking about measurements of particle physics at the CERN Large Hadron Collider, the LHC, and in particular the Higgs boson. Then I'm going to be talking about a technique for exploring possible physics beyond the standard model, which I like very much, which is to treat it as an effective field theory. And I'll be discussing this approach in a bit more detail later on. I will also mention a couple of strange results which are exciting a lot of interest in the particle physics community at the moment, which look like prima facie evidence for physics beyond the standard model. So one is an apparent violation of flavor universality in beam meson decays, and another one is a recent measurement of the anomalous magnetic moment of the muon. And I may, if I have time right at the end, mention another surprise. So on this slide here, there's a compilation by the CMS experiment at CERN of many measurements that they've made of processes involving fundamental particles, W's, Z's, photons, the top quark, and of course the Higgs boson. And as I've highlighted in red here, it's a feature of these data that generally they agree very well with the standard model predictions. So the measurements are shown in different colors and the theory predictions are shown in gray, and in general there's decent agreement. I've circled here in this red oval the measurements of the Higgs, and I'll be focusing a bit more on those in just a moment. So one thing that I would like to emphasize is that these measurements, starting also with the discovery of the Higgs boson, are very much international successes. And in particular, there are groups from several African Arab countries that are now participating in LHC experiments. The pioneers were Morocco on the left and Egypt on the right. And I think it's worth remembering that in order to make progress in fundamental science, international collaboration is absolutely fundamental. And as an example of that, I'd just like to show you this slide. So important components of the CMS detector at the LHC are melted down brass coming from Russian naval shells, which were recycled back in the 1990s to help make the detector. And I'm sorry that the international collaboration in science, which was so strong then, seems to be weaker at the moment. Okay, so what about the measurements of the Higgs boson? So my then PhD student and I wrote in a paper back in 2013 that the new particle discovered almost 10 years ago at the LHC walks and quacks like a Higgs boson. And of course, one of the key predictions of the Higgs boson in the standard model is that since it gives other particles their masses, its couplings to those particles should be proportional to their masses. And this is a plot produced by the CMS experiment, which shows you as a function of the masses of other particles, the strengths of the Higgs boson coupling to them. The standard model predicts this linear rise given by this dashed line, and that is in fantastically good agreement with the experimental measurements. And so, as I said, we wrote in our paper that this particle walks and quacks like a Higgs boson. So Peter Higgs can smile. So, some people might say, well, okay, so the Higgs boson has been discovered. This is the last particle expected within the standard model. Is that an end to particle physics? And I would say no. And I would cite this quotation from a poem by T.S. Eliot called Little Gidding. Little Gidding is a village in England with a beautiful church. Anyway, T.S. Eliot wrote, "To make an end is to make a beginning. The end is where we start from." And that's very much what I feel about particle physics at the moment. So yes, the Higgs boson completes the standard model, but that provides us with a basis for thinking about other physics beyond the standard model, which is going to be the main focus of my talk. So I'm not going to discuss the standard model in any great detail. If you want to see the standard model Lagrangian, you just have to look at my pullover. But what I'm going to do is I'm going to focus on the pieces of the knitting on the pullover that involve the Higgs boson. So here they are outlined in red. So the first term here is how the Higgs boson couples to fundamental fermions psi. These are what we call Yukawa couplings. And as Gerard at Hooft pointed out in his talk earlier on, these couplings seem to be basically random numbers, that we have no theory of what the couplings should be. That means in particular that we have no theory of what the masses of elementary particles should be. We have no theory of why the fundamental quarks mix under the weak interactions in the way that they do. And these are all lumped together in what we physicists call the flavor problem. And this is a very, very deep problem, which I'll be returning to later on in this talk. Then we come to the second term here. So this was also mentioned in Gerard's talk. So this is the fact that the mass of the Higgs boson is much, much smaller than what many people would regard as a natural mass scale in physics, namely the Planck scale associated with quantum gravity. So this parameter mu here is some 17 orders of magnitude smaller, and this raises two questions. First of all, where does this hierarchy of masses come from? And secondly, how do you stabilize that magnitude against radiative corrections, which tend to destabilize it? Then we come to the third term here. So this is the quartic Higgs self-coupling. So this has to be positive in order that the Higgs potential have a minimum. If lambda were negative, there would be no minimum and the theory would be unstable. So the effective value of this quartic coupling at present-day energies is indeed positive. However, as I'll discuss in more detail later on, when you calculate how this coupling changes as a function of scale, you find that it goes not only down to zero, but even, I would say, to negative values before you reach the Planck scale. And this means that formally our electroweak vacuum is unstable. Here I've added in a constant term. So Roger Penrose mentioned this in his talk. It's what's nowadays called dark energy. Of course, it was postulated by Einstein back in 1916. And I personally regard it not as being a mistake, but actually one of his most profound insights that such a term should exist. Then over here in a separate red box, I've written possible additional higher order interactions among the standard model particles. And this will be one of the main themes of my presentation. So in view of its importance and the fact that it's already been mentioned, let's think a little bit about this issue of the stability of the electroweak vacuum, or to express it in simpler terms, the stability of empty space. Now, in the standard model, the stability of empty space depends on the masses of the Higgs boson and the top quark. And in this simple graph here, horizontal axis is the mass of the Higgs boson, the vertical axis is the mass of the top quark. Their masses have now been measured to be about 125 GeV and 173 GeV, respectively. And that puts us apparently in a region of parameter space where radiative corrections, quantum effects, destabilize the vacuum. So the situation is the following. In order to give the observed masses to the elementary particles, the value of the Higgs field, represented along the horizontal scale here, is small but non-zero. Now, according to the calculations in the standard model, there is actually a deeper vacuum where the effective quartic coupling goes negative. And if we were in that region, then the universe would collapse basically in a big crunch. So this raises two issues. One is whether quantum fluctuations could drive us through the potential barrier and into this big crunch at some point in the future. And the other issue is what happened in the very early universe when these fluctuations would have been much bigger, and those fluctuations would have driven most of the universe over into this big crunch 10 to the 10 years ago. So how do we avoid these problems? Well, one possibility is to change the theory at large scales by introducing new physics, and in particular, by introducing an infinite barrier here that you can't tunnel through, which is what happens in the theory of supersymmetry. Now, in view of the importance of this topic and the fact that it was mentioned earlier on, I put in a slide which uses a very, very recent measurement of the mass of the top quark by the CMS experiment that was announced on Tuesday, and that's what's that's shown here. And if you insert that and the measured values of the Higgs mass and the strong interaction coupling into this parametric formula, which has been around now for a few years, then you find that this instability scale, the scale where the potential turns over, is about 10 to the 12 GeV, far, far, far below the Planck scale, apparently. And this, of course, relies on assuming that the standard model is all there is, up to 10 to the 12 GeV. But to my mind, what it indicates is that there must be some new physics appearing before that turnover scale. So what could that new physics be? Well, of course, the classical way to look for new physics is to look for new particles, what you might call the direct method. But the Chinese strategist Sun Tzu, many, many years ago, wrote a treatise in which he said, the direct method may be used, but indirect methods will be needed in order to secure victory. Indirect here, I think, means quantum effects of unseen particles. The direct and the indirect lead onto each other in turn. It's like moving in a circle. Maybe he was thinking of a circular collider. Who can exhaust the possibilities of their combination? So what do I mean by the indirect method? And by this, I mean using effective field theories. So if you go back to the 1930s, we had a sort of embryonic standard model of electrodynamics based on couplings between electrons and photons, which had dimension 4. And subsequently, we learned how to renormalize and do very detailed calculations. But in parallel, Fermi proposed a 4-fermion effective field theory of the weak force, which involved 4 fermions interacting at a point. Now that sort of interaction has dimension 6, and it's non-renormalizable. You can't do higher order calculations. Now for some 20 years or so, there was a discussion about the precise form of those interactions, whether it was scalar, pseudoscalar, vector axial, what have you. But there was a general feeling that this sort of interaction was probably due to the exchanges of massive particles. And when in the 1950s, it was realized that that interaction was effectively the interaction of two V-A currents, people said, aha, the exchanged particle should be a vector particle. And so that led people to start thinking very seriously about how to make a theory with massive vector bosons. And that led, of course, to spontaneous symmetry breaking and the Higgs and the Standard Model. In parallel, Yukawa postulated that the strong nucleon force was due to the exchanges of mesons, the lightest one of which is the pion. And then when people looked at the dynamics of the pions, they discovered they had a very particular form. In fact, they have a form of chiral dynamics, to make a connection with the previous talk. And that chiral dynamics was an important clue leading us towards QCD. So these two instances indicate how, by looking for effective interactions beyond what was the standard model of the time, you can hope to get some insight into what the theory beyond the standard model might be, in this case, QCD or gauge theory. So we're in a somewhat similar situation at the moment. What we do is we assume that the standard model Lagrangian is correct, as written on the pullover, but we say that it's incomplete, and we look for possible additional interactions between